on any question that you have, and just react for me to be able to see that there's actually a question that any of you guys have. Cool. Okay. Let me just verify that everyone is in. All right, so I'm about to start. So if I can just get one more round of like a reaction just to make sure that we're on the same page just before I start. Okay, a few more. And the other guys, can I just assume that you guys are ready for me to start now? Okay, cool. So, like I mentioned, we have a lot of material to cover. And one thing, guys, that you have to note about 2004 is that in many cases, you will find that, in many cases, you would find that the questions could be easier, but then there are just a little tricks that there are a few tricks that you just have to factor in to make the answering the question much easier, right? And there are a few things that I'm going to quickly write at the beginning of this workshop, some things that I would like you to refer to, which you'll most likely be using a lot, but will not have a lot of time to go through all of those things. The first one, unlike the last workshop we did, we went through double integration to start with. So can you just find some time to go over through your double integration? I'm talking about integration by substitution and all those kind of stuff. And there are many other cases when you are going to, it's going to be a very simple question, for example, when you're looking at a simulation problem, right? But which involves you playing around with your CDF, but getting that CDF can be a bit difficult. And some of the tricks that could be done there is giving you a CDF which you do not know and you've never seen before. For example, I'm talking about a Pareto distribution or a Gumbel distribution. I remember in my test one, in when I did 2004, we had a CDF where we had a PDF actually, and we had to integrate the Gumbel distribution. This is something that you can obviously do in a test, but if you get a chance to actually look at this kind of distributions beforehand and just play around with them and be comfortable, it makes it easier and you'll be able to answer the questions more easily. Also, just look at your Pascal triangles, because there comes times where, especially when you're doing questions under your ketosis and your skewness, this will definitely become useful in being able to simplify your answers, right? And one other property which is important is this, which says that e to the power x is equal to the summation, right, along x of x to the power k over k factorial. Rather, this is the summation over k. This is something that is more than once actually very useful. Something else we find useful is this of a binomial series, which says that x plus y to the power, this is x plus y to the power n is equal to the summation from k equal to 0 to n of n choose k, x, k, y, n minus k. I understand this might not make sense right now, but I will refer as to when we are going to be using these things here. Some of them we may not use them in today's workshop, but maybe tomorrow in the second workshop. But this, whatever I'm going to write now, is definitely something which will make some questions that seem complicated much easier. Then this other one, this is definitely something we'll use tomorrow when we are dealing with convergence, which says that the limit as n goes to infinity of 1 plus x over n or to the power n is simply just equal to e to the power x. And this is one of the things which are important. Cool. And something else that you can look at is our logistic function. So the functions that I've put here, the three that I've put here, these are just, when you get time, look at the CDFs and the PDFs, make sure you're comfortable from moving from the PDF going to the CDF and also backwards. Okay, cool. So those are just some of the few things which I feel are very important for you to revise them. Probably things you've seen before. It's just a matter of you going over them. All right. Oh, one more thing is that as you can see, my board space is quite limited. So I hope you'll be able to keep up with me in writing, because I will be actually wrapping the works that's on the board so that I can write something else that's you. So before I wrap this, just to make sure that you guys are still with me, can I just get a reaction to know that it's okay for me to wrap this that's on the board quickly? Cool. All right, one sec. I'll just wait quickly for a second for someone. Then after this year, then we're going to probably start now. These are just some stuff that I thought maybe I should let you know that you need to watch out for them. Cool. So, Bonam, can I continue now? Cool. I am going to assume it's okay now, and I will move on. All right. Cool. Sure. I will go on now. So now we can start. So as we start, when you look at your notes, we're considering a random variable x, right? Specifically today, we'll be looking at the univariate case, right? So all we'll be doing is focused on this x here, a random variable, right? And there are many things that we're interested about this random variable x that we have here. We're interested in its distribution, its mean, its variance, and all these things that we're interested in are there, even other stuff, right? Our ketosis, our skewness, and all these properties that we'll be considering here are all based on what we would find our distribution of x to be, right? So the main focus at the beginning is all about finding the distribution of x. That is, we're looking at the CDF of our random variable, our CDF as being the first focus of the random variable, right? And we know by now that the CDF of a random variable x here, right, is defined as being the probability that our random variable x is less or equal than some constant x, like that. So this is what we know so far about the definition of our CDF of the random variable x. And from this here, which we're going to cover again, you'll be able to even find the density of your CDF, right? And from there, you'll be able to find any other property that you would like, either it be the mean or the variance. When you go through your notes, you'll find that there's a number of properties that are given about a CDF of a random variable. One of the most important being that if you want to find this CDF, suppose you've got your density, right? And you want to find your CDF. You find your CDF of x, right? By integrating from the lower bound to x, your PDF with respect to x. So this is how you would find your CDF of x, right? And right from that, what's also very important, what you use more than quite a lot, especially when you want to apply the Darth-Vader law when we get to it, is the survival function, which is s of x, like this. And your survival function is simply just described as 1 minus your CDF of x, like this. And if you wanted to find your survival function manually, the same way that we find our CDF of x by integrating from minus infinity to x here, this minus infinity being the lower bound, when you want to find the survival function, what you will do is actually you integrating now from x but going to infinity, and what you'll be integrating here is your PDF of x, which will be given, and this will be done with respect to x. So just to quickly go over the difference between these two integrations that I've done here. The first one, you're finding the CDF of your random variable, right? And you integrate from minus infinity, the lower bound, to x, and you're integrating your PDF. When you want the survival function, which is simply 1 minus the CDF that you have there, you now be integrating from the bottom going upwards to infinity. One other characteristic of CDF is that when you want to find the probability that your x random variable is between A and B, this is simply equal to you saying f of B minus f of A, like this. What this means is that if you've got a random variable a, x, which you've got its CDF, if you want the probability that your x is between a and b, all you have to do is to take your CDF evaluated at b minus the CDF of x evaluated at a. Then I'm going to quickly move on from the CDF there to introduce what we call an indicator function. An indicator function. This is something as well that when you actually have a simple question, this is something that can actually make your problem look more complicated than it is. An indicator function is defined as follows. If you've got an indicator function and you have a here and x, this is simply telling us that whatever you will be dealing with will be equal to, your indicator function will be 1 if x is an element of a and will be 0 otherwise. I'll quickly just talk more about this indicator function. So what we've done here is to describe our CDF of our random variable x, right? And then what follows is an indicator function, which I am saying it's very important for you to understand what an indicator function is, because in most cases, your CDF could actually be defined in terms of an indicator function, which makes it look more complicated than it is. But by understanding what an indicator function, you're able to simplify your CDF into something that you can easily work with. Right, I'll quickly give an example on how to do this. But all an indicator function tells us is that if your indicator function is defined as follows, as a and an x there, this will be equal to 1 if x is an element of whatever interval that you may be given here as a. And if x is not an element of this here, then your indicator function will thus be equal to 0. All right, I'm going to quickly wrap this part here. And then we are going to discuss the types of random variables, right? That follows the types of random variables, right? One of the most obvious ones that we start with being our discrete. We have our discrete random variable, right? And we know by now this is the one where you use a summation. Because the two distinct random variables that we have is the continuous one and the discrete one. The discrete one is the one where you will be doing your summations, where the PMF is given as the probability that the PMF of x is simply equal to the probability that x is equal to x. Because this one is counting when we're considering the x values 0, 1, 2, 3. Then the one that follows from that one is the continuous one, the continuous random variable, right? This one, as the name says, is continuous. So it deals with numbers that are like 0.1, 0.2, because it's continuous. If it's defined between 1 and 2, it considers all the numbers that are in between 1 and 2. And you say a random variable is continuous if the CDF itself is continuous. So in a case where you're asked if the random variable x is continuous, if you say that its CDF, maybe for an exponential distribution, if its CDF is continuous, then you can conclude that the random variable itself also is continuous. Then you have the absolutely continuous one. Absolutely continuous random variable. Absolutely continuous random variable. And this one, there's one example that we're going to look at where I am going to show you on how you show if a random variable is absolutely continuous. Because it can happen that maybe a question will ask you to find the CDF of some random variable. Then the follow-up question, which I've seen like in your past OTs, the question could be then asking you if x is absolutely continuous or not. I'll go over on how you will show that a random variable is absolutely continuous. Then the next one is a uniform distribution, right? And then this one here, I'm going to quickly just write a little bit more on this one because it's important. And the CDF of a uniform distribution is simply equal to 1 over the length on which the random variable is said to be uniform on. So what I mean by that is that if you're given information about a random variable x, suppose we have a random variable x, and we're told that this is uniform between A and B. What this statement I have here is saying is that the PDF of this random variable will simply be equal to 1 over B minus A. Because it says this is equal to 1 over the length of the interval on which we are saying this random variable is uniform on. So this is something that is really important. We'll also look at a bivariate case on what actually then happens to this denominator when you're dealing with the two random variables. Cool. Then the next one, which is the most interesting one when you're dealing with this section, especially the first, between the first and the second chapter, this is the most important one, which is the mixture distribution. This one is a mixture distribution, right? What I mean by this is that this one is neither a discrete random variable and it's also not a continuous random variable. Cool. And for now, this is what we're going to be mainly focusing on until we get to the one where we focus on just the discrete and the continuous. We'll be looking at random variables which are not specifically told to be either continuous or discrete, but rather these are the kind of distributions which will be more defined in terms of an indicator function. Cool. So I am going to, let's quickly look at this here, some examples. Suppose that you've got x exponentially distributed with lambda. Obviously, this is a continuous case, but now we're going to define another random variable, right? Y. Let's have y being equal to x, and now we have an indicator function here, and we have x being greater than 5, like that, right? So what you need to do from after this now is that, like I mentioned earlier on, you will often be given a distribution or maybe a random variable which is defined in terms of an indicator function. This is just to throw you off. But whenever you're given a random variable which has an indicator function, the first thing that you must do is to break it down or simplify it, if I can say, right? Remember, as we defined an indicator function earlier on, we said an indicator function L, and I have an x here, is defined as follows, that this is equal to 1 if x is an element of A and is 0 otherwise, right? Is 0 otherwise. So when we're given a random variable y, which we are told that is equal to x, when the indicator function, an indicator function like this, x greater than 5, this means that our y will simply be equal to x if x is greater than 5 and will be equal to 0 otherwise. Otherwise, right? So if you wanted to write it completely, instead of writing otherwise here, we know that this will be equal to 0 when x is less or equal than 5. This is why this is very important that you understand how to simplify this. Because we're going to do a lot of examples where you being able to simplify this here will make whatever you do there much easier for yourself. Before I go into a more complicated example which deals with indicator functions, can I just get a reaction to show that everyone is okay with what we've done so far? Okay, cool. Awesome. That's actually the first time that everyone is answered in this group. Cool. And then before I go to this example that I want us to do, there's something that we might need to use at some point that I want us to quickly go over. Now, I will remove this. Cool. I just wanted to quickly go over some notes, some theory on the gamma and the beta distribution. The beta distribution. The gamma, I'm going to start with my gamma distribution. So whenever you're given information, maybe they give you parameters. That's what you're most likely to get. You are given the parameters of a gamma distribution and they ask you to find the CDF. This is the formula you always use when you want to find the CDF of a gamma distribution. This is defined as integrating from 0 to infinity of t to the power x minus 1 e to the power minus t dt. So whatever question that you may have, which is asking you to find the CDF of a gamma distribution, this is what you find to find the CDF. Then there's this nice property about the gamma distribution, which says that gamma of n plus 1 is equal to, gamma of n plus 1 is equal to, you take this n that you have here, then you take it out and you'll be left with still gamma n, like this. This property only applies if you've got a 1, like that there. This means that if I have gamma 3, for me to be able to apply this property, I need to write this as gamma 3 plus 1, right? And the same way that I had n plus 1 there, I would take my n out. In this case now it's my 3. So what I would have here is 3 gamma 3, like this. right? So again, the reason I did this here, oh, sorry, my bad. What I wanted to emphasize on is that when you have gamma n plus 1, right, what you do is to take this n out and you'll be left still with the gamma n inside there, right? So when you've got gamma 3, what you have to do is to write it as gamma 2 plus 1, because we've not changed anything here. You still have gamma 3 as 2 plus 1 is equal to 3. The reason you do this is that this property only applies when you have gamma n plus 1. So whatever you're adding with here, but the other term has to be equal to 1, right? And the same way we took the n out here, what you take out in this case will now be a 2, and then this here will be gamma 2. And you continue, what I mean is that you would have 2, then you now have gamma 1 plus 1, so that this will just be equal to 2 gamma 1. And gamma 1 is defined, I think it's actually given, the value of it is given in the notes. Then you just find your answer from there. All right. Then the next thing about gamma distribution is that now if you want the PDF of the gamma distribution, right? So suppose X has got a gamma distribution with the parameters alpha and lambda, like that. For you to find your PDF of the distribution of your gamma, this will now just be equal to the f of x will be equal to lambda to the power alpha x alpha minus 1 e to the power minus that over gamma this, right? And one more thing, this is not really something for you to stress about much, like to remember what this is and what that is. These are stuff that you'll find on your formula sheet, but it's really just important for you to know them, because there are many cases where you will need to be able to spot this. And when you know it already, it will be much easier for you to spot it on in a question than for you to first have to go to a formula sheet. Because going to your formula sheet, right, is just for you to verify that it is correct. But in order for you to be able to quickly spot on that, okay, fine, this is the gamma distribution, just try to get familiar with how you write this distribution. Cool. And then for our beta distribution, before I go to the beta one, there's a special case of a gamma distribution, right, which tells us that if X has got a gamma distribution, right, and the parameters that you have is 1 as to 1, then you can conclude that this X here actually has an exponential distribution with lambda equal to 1. So an exponential distribution here, this only proves that an exponential distribution is a special case of a gamma distribution, if only the parameters that you have there are both 1. Another special case is that if X has got a gamma distribution, and the parameters you have is n over 2 and half, like this, right? It follows straight from that your X, this X that you have here, right, also has a chi-squared distribution with n degrees of freedom. And I want you to say that this n here corresponds to this n that you have there. So what this is saying, just to go over it again, is that when you've got an x random variable, right, and it's got a gamma distribution with parameter n over 2 and half, right, this we can also translate it as being an x random variable which has got a chi-square distribution with n degrees of freedom. This is very important, as a question can either come in the form that suppose we've got a random variable x which has got a chi-square distribution and n degrees of freedom. From there, you'll be able to know that you can actually just go backwards and know that you're actually just dealing with a gamma distribution that has got n over 2 and half as the parameters. And even to make it better, you can move from this to that, and also to then conclude that this random variable x is in fact just an exponential distribution which has got lambda equal to half. This has got an exponential distribution with lambda equal to half. So a question which can start by telling you that suppose you've got a random variable x which has got a chi-square distribution with n degrees of freedom, right? If you're not comfortable with working in this manner, which is very difficult, so instead you can use this as being what? This is the gamma distribution that has got n degrees of freedom, right? So this parameter will be n over 2. So in a case where an example, this is actually a chi-square distribution with let's say 10 degrees of freedom. This means your gamma distribution will be something that is for 10 over 2, which is 5, and your alpha and your lambda being half in there. And again, now, if you're not comfortable, also then from that, it means if you want the CDF, you can then apply this to this formula that you have there. If you want the PDF, you can then apply this to the PDF definition that we have right here. But then again, if you're not comfortable with dealing with the gamma distribution, then you can translate this X random variable, which has got this gamma distribution, into simply being something that has got an exponential distribution with lambda half, where this lambda half is actually just coming from this half that you have there. So this n and this n relate to each other, and then this half relates to that half. And this is the best way to work with, because guys, an exponential distribution is literally the easiest, okay, at least to me, the easiest distribution that you can work with, because it's continuous and it's very much easy to work with continuous cases, because it's just a matter of integrating, unlike a discrete case with summation, which is something that we actually hardly do. Cool. Then I want us to quickly go over the beta distribution. The beta distribution, which is also something that you, as much as you can find its definitions on your formula sheet, it's something to get comfortable with, because you being able to notice it quickly from a distribution is important. Because like there are rare cases where you'll be told that this is a beta distribution. There are cases where you definitely be told, but there are times where it's very important for you to be able to realize that, okay, what I want to find here is maybe the nth moment, right? Using the law of the unconscious decision, something we're still going to talk about, you would have to multiply the distribution and integrate it. When you're doing that multiplication there within your integration, it is then where you're required to be able to see that when you do the multiplication, what comes out, is it a gamma distribution or is it a beta distribution? Again, this is just moving forward. We're still going to go to that, and I'll point it out as to when you need to be able to identify this distribution. So suppose we've got a beta distribution. The definition of a beta distribution, which is the parameters m and n, is the same as the beta distribution with n, m, like this, right? And this is defined as you integrating from 0 to 1, and you have t, m minus 1, 1 minus t, and n minus 1, like that. This is what, with respect to t, like that. This is the definition of a beta distribution. And as you can see, this is something that is between 1 and 0 and 1. I am seeing, a question in the group which was asking about the first equation. Oh, guys, when you've got a question, can you just give me a reaction in the reaction so that I can also quickly see that there's a question there. So the first question was asking if the first equation was that of the distribution, or the CDF of the distribution of the gamma distribution. This is the CDF of a gamma distribution, the one that I had here initially. So if maybe you're given information about this distribution, suppose X has got a gamma distribution, something like this, and then they give you some parameters. I'll just write alpha and lambda like this here, right? If you want to find the CDF, this is the formula that you use. You're integrating from 0 to infinity, and t to the power x minus 1, and e to the power minus t dt, like that. This is what you would use when you want to find the CDF of your gamma distribution. And obviously, it's just that now the parameters will be more specific. Here, the parameters that are used here are not consistent with what I've put here. But again, I will try to find, I'm trying an example which will clarify exactly as to how you use this definition to find the CDF of your gamma distribution. But the main point you take from that is that if you're given information about a random variable, which you're told is called a gamma distribution, this is how you would find your CDF of the random variable. Okay, I hope that answers the question. Can I just get a reaction if that's okay from the person who asked the question? Okay, I'm gonna assume that it makes sense. Anyway, I'll get back to it and then hopefully to make sense there. Cool. And then, one more important thing that's important about this here, that this beta distribution definition is equal to this. This is also then just equal to gamma n, gamma m over the gamma of n plus m, like this. And in the special case of our beta distribution is as follows: that when x has got a beta distribution, right, and the parameters are both 1 and 1, this is simply just your x having a uniform distribution between 0 and 1, like that. Cool. So what I'm saying, just to go over that again, what I'm saying is that you have your beta distribution like this, and then this is how it's defined, right? And in a case where you are given that your beta distribution actually has the parameters 1 and 1, if you're not comfortable with working with what we have here, you can rather just treat this here as a random variable that has got uniformly distributed between 0 and 1. And remember, like we mentioned earlier on, when you're now dealing with a uniform distribution, it is then much easier to find its PDF, because this will literally just be equal to 1 over the length of the interval. And if you're dealing with between 0 and 1, the length there is 1. So the PDF of x in this case now will simply just be equal to 1, which is something that is very easy for you to work on. Cool. I am going to quickly go backwards, right, to when we're dealing with the distributions, which are neither continuous or discrete, the mixture, and also a combination of indicator functions, so that we can get a proper feel on how you answer those kind of questions. And the first thing, here's the example. I'll call it our example 1, right? And then the information we have is that suppose we've got a random variable x, right, which has got a chi-square distribution with 2 degrees of freedom, right? Remember, what I said is that when you're given a distribution like this here, which you're told has got a chi-square distribution with n degrees of freedom, just that in this case, our n is equal to 2. We can translate this to a gamma distribution, right? This here means that our x actually has a gamma distribution, right, with parameters where we had n, this would be 2 over 2, and we're going to have a half, right? So if you want, remember we have a definition of a PDF of a gamma distribution. So straight from this here, you can then go and work with a PDF of a gamma distribution. But if you want to make your life easier for yourself, you can then translate this here from being a gamma distribution into being an exponential distribution, which we know that this would mean that our x here actually just has an exponential distribution, and the parameter for this here, this lambda, will be this half that we have here. So now what we actually just have is an exponential distribution with our lambda being equal to half, right? And straight from there, it could be the first thing that you might want to do, that you can now just find the CDF. Find the CDF of your x, which is just the CDF of x here is just going to be 1 minus e to the power minus half x, right? This is your CDF of x. Cool. Just give me a second. You guys can see me, right? So just hold on a bit, hold on a little bit. Don't know what's happening. You guys still cannot see me, right? What we had before this whole thing happened is that we were given a random variable x, right? We were given a random variable x here, which is for a chi-square distribution with 2 degrees of freedom. And we all agree that from that, it's quite difficult for us to work from there. So the first thing we did was to translate this into a gamma distribution with these parameters. And then we can even further go on to translate it into an x random variable, which is for an exponential distribution with our lambda equal to f. And then from there, the best thing that we can then get from that is just the CDF of x, which as we have here is 1 minus e to the power minus half. Then what would follow is that you can then get another random variable, because remember what I said, what I want us to quickly focus on, which is what you're most likely to get from the first 2 chapters there, is a random variable which is neither continuous or discrete. That is something that is like a y being equal to 2x. You've got an indicator function there, and x is less than 4 plus 4. You've got x and an indicator function, which here is x minus x greater than 8, like this, right? So the question starts as like this here. You're given information about another random variable x. This is something we'll look more deeper into when we get to transformations, because now you've got a random variable x here, and then now you're given y, another random variable in terms of that x. I'm just going to quickly say what it is in case some of you may not be able to see this properly on the board. But what this is saying, this is y being equal to 2x, indicator function, and our x is less than 4, plus 4, x, indicator function, x being greater than 4. So whenever you've got a question like this, right, the first thing that you must do is to break down or simplify the indicator functions like we mentioned earlier. So the step one, our step one here will be for us to simplify the indicator function. So your step one, right, is simplify. I'm just going to write simplify. But what I mean is for us to simplify the indicator function. That is to break it down into something that makes more sense for us to work with, right? So what this is simply telling us is that your y, this y random variable that you are given here, this here is just equal to 2x when x is less than 4, and 0 when x is between 4 and 8. And then this is equal to 4x when your x is greater than 8. I'm going to quickly explain this again. Our indicator function here was given as follows. 2x, we have an indicator function, and x less than 4. What this is telling us is that when you're on your interval of a random variable, whenever your x here, this x random variable that you have here, whenever it's less than 4, then your y is equal to 2x. Hence, I wrote 2x when x is less than 4. then what follows is it telling us that when your x is greater than 8, it's also quite important, guys, for you to pay attention to whether it says less or equal than in this case here. Whether it's greater or equal than does not really matter when you're dealing with a continuous random variable. But as you can see, this y random variable here is neither continuous or discrete. So it's very important for you to note on whether this here is saying when x is less or equal than 4 or otherwise. Oh, okay. The reason why there's a question in the group which is asking why the bounds have got a small x and the little x. This is because, right, this random variable here, for example, it's as it is, it's an exponential distribution, right? If I were to write the PDF of this here, this would be f of x, right, being equal to e minus half x. Okay. Let me define the CDF itself. This is the CDF of x, right, is equal to, this is equal to 1 minus e to the power minus half x, right, when x is greater or equal than 0, and this is 0 otherwise, right? So these x values that I'm referring to, these are x values which are defined when you're defining the random variable x as it is, right? Because remember, as much as we are dealing with these are random variables, but this here is just defining intervals on the real number line. Hence, I write a small letter x. The small letter x always represents constants. These are just numbers on your real number line. Hence, when I'm dealing with numbers, they're defining what this distribution is, the random part of it, but on the number line. Hence, I'm using the small letters x like this. Because even, maybe I guess why your question could have been, this here on its own as well, these are small letter x's. Maybe just the way I wrote it, right? So this is saying that y is equal to 2x, right? When on the interval, your x which you have here, the x values that you have, which are defined in this x random variable here, are less than 4. That's what it's simply just saying. Cool. I hope that answers the question. So if I were to continue, so our y now, we've broken it down to something that's simple and something that we can use from what we initially had there, which is what indicator function. So that must always be your first step whenever you get something that's like that. Cool. That's something that you must always do when you get a question like this, is that you firstly break down from the indicator function into something that you can use. Then your step two is that find the CDF of x, right? This is something that we've already done there. We have our CDF of x, which is equal to 1 minus e to the power minus, our lambda is given as half here, and we have that. And the reason why we find the CDF of x, right, is already, as you can imagine, if our y is given in terms of x, is whatever distribution of y we are going to get will have some relationship to the CDF of x. So what I'm simply just doing here is in advance already getting the CDF of x, because we are definitely sure that at some point we are going to use it, right? And in a case where maybe you make some mistakes later on, having done this already will give you some marks. Defining the y like in a simplified manner that it is an indicator function, and knowing that, okay, my x is from this to this exponential, and now you've got a distribution for that. That is why sometimes it's quite important for you to do this here step by step, as each step should actually give you some mark, or even if it's just going to be half a mark, depending on what exactly that step is, right? So step one, you simplify your indicator function. Step two, you find the CDF of x. In this case here, x is the CDF of the random variable whose information we already have, right? Which is the x random variable whose information we were given initially. Your step three, oh, sorry, by the way, I did not explain what we are trying to find here. The question here would be that find the CDF of y. That's what we want. We're given information about the random variable x, and extra information about it. Then we are given y, but in terms of x, and the question is now saying find the CDF of y. So all these steps that we are taking here are just steps for us to get to the CDF of y. So now your step three would then be use the definition of a CDF. So I'm going to write definition. I will write definition of CDF. So now the next thing, what you have to do, remember we want the CDF of x. So this step, what it's saying is that use the definition of a CDF for us to find the CDF of y. So we want the CDF of y, and by saying use the CDF of the definition of a CDF, what I mean is that then write that the CDF of y is simply just equal to the probability that the random variable y is less or equal than y, like this. That's what the third step should be there. Then what follows from the third step is your fourth step, our step 4. And what step 4 tells us to do is that use the law of total probability. Law of total probability. You don't really have to specify that, okay, you're using a law of total probability. This is something you definitely have been doing, but maybe not named it yet. But the reason why I decided to write this is because I've seen a question where he gives a hint to be like, use the law of total probability. So if you don't really know that what you've been doing is the law of total probability, you may then now get worried as to how you are supposed to use the law of total probability. And the law of total probability says that the probability of A is simply just equal to the probability of A intersecting with B plus the probability of A intersecting with B complement, right? So in this case here that we have, our B is simply just representing an interval, right? So if I'm looking at a case where maybe X is less than 4, its complement will be a case where X is greater than 4. Yeah. Cool. Yeah. So this is our law of total probability, right? Given as follows. Then now what we simply just have to do is to use the definition of our CDF and together with the law of total probability to then find the CDF of our random variable y. What we then do is that, so this is still under my step 4, what I would do, the CDF of y, right, which is defined as the probability that y is less or equal than y, right? Then this here will be equal to, remember, this is very important, and I hope you've written this down because after my ideal space, I might have to wrap this part. Time to time, we have to come back and refer to this. Cool. So what this is saying is that now I have my definition of a CDF there as it is. I've written it down. The next thing is for me to then use the law of total probability to try and find my CDF. So what I would do is that this is equal to the probability that y is less or equal than y, but now I am going to intersect it with my first interval that I have here. That is when my x is less than 4. So this is the probability that y is less or equal than y intersecting with my x being less than 4, like this here. Then I close my bracket there, plus, right? Because remember, this law of total probability, it should cover every interval that you have there. And if you look at this, our intervals that we have is when x is less than 4, then being between 4 and 8, and x being greater than 8. So the first part here is taking care of the part where our x is less than 4 by taking the definition of our CDF, which is here, and now I'm going to take this to the intersection of one interval that I have there, which is when x is less than 4. Then I will carry on to say plus the probability that y is less or equal than y intersecting with my second interval now. This is when my x is between 4 and 8. So this is 4, I have a 4 here, and I have being less than x being less than 8, like this, plus, again, the definition, the probability that y is less or equal than y intersecting with the other interval now where my x is greater than 8, like that. Cool. Again, it's very important, like I mentioned earlier on, for you to see from the definition of your indicator function there on whether this is x less or equal than 4 or it's just x less than 4. Cool. I'm going to assume that everything is okay. And then we move forward to our step 5, right? I hope you wrote this down here because what we're going to do now is going to be referring to this definition that we have here. I have it on my paper here, so I will be looking at that. And then you can go back, you can look at what you have written by now. So the lesson that we have here is our law of total probability. in with these three terms here, where we have our definition intersecting with the first part of the interval, the second part of the interval, and the third part of the interval. And the next thing that you should then do from that, right, our step five is for you to consider what your random variable y is under each interval. Cool. What I mean by this is that, okay, I'm just going to write equal sign because I am continuing from that. Right? What I mean by saying consider what our interval is, our y is under each interval, is that the first part of this, the first term of this line here, which is the probability that y is less or equal than y, intersecting that x is less than 4. What I mean by this is that now look at the interval when x is less than 4 and look at what y is in that case. If you would have written it down, initially we wrote that, okay, I think I need to write this down so that we can all refer to it from the board. We wrote earlier on that y is equal to 2x when x is less than 4, right? And we have 0 when x is between 4 and 8, and we have 4x when x is greater than 8. So what I mean by saying consider what y is under each interval is that now we know that when x is less than 4, our y is equal to 2x. This means now, I am continuing from there, this means now when I write this statement now, this will be equal to the probability that instead of writing y, I know that when x is less than 4, my y is equal to 2x. So instead of writing a y here, I would have, this is the probability that 2x is less or equal than y, intersecting with my x less than 4, like this, and I'll close my bracket, plus the probability of when x is between 4 and 0, we know that this is equal to 0. Between 4 and 8, right, we know our y is equal to 0. So instead of writing this y here, I'm going to write that this is the probability that 0 is less or equal than y, intersecting with 4 being between x and 8, like that. Plus, instead of writing my y here, this is telling me that when x is greater than 8, my y is equal to 4x. So instead of writing the probability of y being less than y, this will be the probability of 4x being less or equal than y, intersecting with the fact that our x is now greater than 8. Cool. That is what the step 5 tells us to do, that you just now have to consider what your random variable is under each interval, and then you substitute into what you have gotten in your step 3 here. Okay, I will continue this statement from this side of the board now. And the next thing that follows is just simple maths, because now we are saying this is the probability that 2x is less than y, right? So what you then do is to say this is equal to the probability that instead of writing my 2x here, you try to make x the subject of the formula on the left-hand side. And the reason is that, remember, when we're studying this question here, we're given information about x, right? And we're able to find the CDF of x, and we all agreed that since our random variable y is given in terms of x, right, whatever CDF we get of y would have some relationship to x. So what we're actually trying to do here is to find something that is in terms of x, right? Because we have information about x already. That is why when you get to this point here, we are going to come back to this these terms here, and instead of writing as it is, we are going to write it in terms of x. What I mean is that instead of having the probability of 2x being less or equal than y, we are going to have the probability of x being less or equal than y over 2, right? All I've done here is to divide by 2 both sides, and now I have the probability of x being less than y over 2 intersecting with x being less than 4, all right? Plus, now if you consider the second term, this is the first one that we're going to kind of make it shorter. What this is saying is that this is the probability, right, of 0 being less than y intersecting with x being between 4 and 8, right? What this means is that if I were to draw a timeline of some sort, is that I have my number 4 here and I have my number 8.
So this statement is saying my x is between 4 and 8, right? Then this one is saying that 0 is less than y. What this means, in other words, is that y is greater or equal than 0. So what we know is that y is just positive, moving from 0 going all the way to infinity. So if this was 0, our y is starting from this point and it's just going all the way to infinity. But the statement here wants the intersection between y, which starts from 0 going all to infinity, and then also when x is just between 0 and 4. And I'm sure we can all agree that that intersection is simply just here. This is the only part where they overlap, which means if I were to simplify this part here, which says the probability that the probability of 0 being less or equal than y intersecting with x being between 4 and 8, this will simply just be equal to the probability. This will simply just be the probability that x is between 4 and 8, like that. So I've gotten rid of this 0 part here to simplify that to simply just being the probability that x is between 0 and 8. Remember, this happens simply because what we want there is our intersections, right? We are still going to do the same with the first part there and the third part, but just that there's extra stuff that we first need to do for these other terms here. As what I've done here, making x a subject with the formula there, which means even for the third term here, this will be plus the probability. Instead of me writing 4x, I want x to be the subject of the formula. So this will be the probability that x is less or equal than y over 4. And this is intersecting with my x being greater than 8, like this. So this is what we now have. Instead of having something which has got 2x and whatnot, we have used what y is between certain intervals to get this, and we've simplified this to give us terms like this here. Because what we want is something that's going to be much easier for us to work with, right? Now, the next thing that follows is for us to get to the same way with the green part here, what the green term, we want to do what we did to this to the rest of the other terms there, which means that this here will be equal to, now, the first term is saying this is equal to the probability that x is less than y over 2 intersecting with x being less than 4, right? I'm going to quickly draw something here. One number that we'll show off is 4, right? We know for sure that there's this number 4 that we have here, and we're told that x is less than 4. It's very important here, guys, that it says x is less than 4, not less or equal than 4. So it means that the number 4 here is not included. And remember that if I've got two things, right? Suppose I have two things, one that is running from 1 to 10, then I have something that is running from 1 to 5. When I want the intersection, I will take where the smaller one ends, right? What this means is that if A runs from 1 to 10, and then B runs from 1 to 5, the intersection is simply 1 to 5, because this is where they overlap, right? So that means if I were to ask you for the intersection of A and B, right, where A is moving from 1 to 10 and B is moving from 1 to 5, right, the intersection there will be the smaller one, which means the intersection is the minimum of A and B, right? And the reason why I'm saying that is because here we want the intersection of x being less than y over 2 and x being less than 4. So what we know for sure is that here x is less than 4, yes, and x is also less or equal than y over 2. But we do not know what the value of y is there. And like the example I just gave now of A and B, where one is running from 1 to 10 and the other one from 1 to 5, we would want the intersection is simply the minimum of those two. This means that instead of having the probability of x less than y over 2 intersecting with x being less than 4, this will simply be just the probability of x being less or equal than the minimum of y over 2 and 4, right? Because right now, we are not sure yet which one is smaller. Our y could be 10, and then that would mean that 10 over 2 will be 5. So in that case, our 4 will be the minimum, or maybe our y is simply just equal to 2, and 2 divided by 2 will be 1, and in that case, our y over 2 will be the minimum. But again, we do not know what the value of y is. So for now, we leave this statement as follows, that x is the probability of x being less or equal than the minimum of these two here. And the second part, we've already shortened that. It's just the probability of our x being between 4 and 8, plus the second part, for now, we can just leave it as it is here because, okay, you understand why later when we simplify it. For now, this we can just leave it like that. Cool. So that's what we have so far. And now we are going to actually then start writing what the CDF of Y is. Because we've spent quite a lot of time on this question, but again, this is the kind of question that if it comes up, it will come up with 10 marks. So you really need to try to be as comfortable as you can with the question. So the first thing that we will look at is this, right? We'll look at the first part. Oh, another thing is that when you then write the CDF of Y, you also need to make sure that even your intervals now, instead of them being in terms of X, they must also now be in terms of your Y. If I can quickly just write what we had initially, because I will need to refer to this, you must have this by now, that our Y was equal to 2X when X was less than 4, and then this was 0 when we were between X and 8, and then this was 4X when X was greater than 8. The first thing I want us to look at is like I said now, what we want is the CDF of Y. And this is all in an attempt to get the CDF of Y. Okay? So this means that even your intervals will now be in terms of Y. Okay? So in this first part here, we have that X was less than 4. X was less than 4, right? But now we are dealing with Y, and we know that when X is less than 4, our Y is equal to 2X, right? So where we had X being less than 4, now we know that when X is less than 4, our Y is equal to 2X, right? Which means here our X is equal to Y over 2. So instead of having X being less than 4, what I would instead have is that Y over 2 is less than 4. And then if I were to multiply there, this means that Y is less than 8. So what I would have here is that my Y is less than 8 as my first interval. I'll quickly just go back on this here because this is very important. These are marks on their own, probably like 2 marks on its own. So what I'm saying is that now, remember what we are doing here, it's just that I don't have enough board spaces, so I don't have the question anymore where it started. But what we are trying to do here is to find the CDF of Y, which is given in terms of X, right? And this X here, remember when we had this here, our intervals are in terms of X. But now that we want the final CDF, like we're getting towards the end, we want our intervals to be in terms of our Y's, right? But we know that for the first interval here, because this Y less than 8 is this part if we're dealing with X, right? Or if we're going back to just the simple definition that we had initially. This here and that are related. How? In this manner. Remember, this is telling us that when X is less than 4, our Y is equal to 2X, right? So Y was equal to 2X when X was less than 4. If I were to make X the subject of the formula here, this simply means that here X is equal to Y over 2. So instead of me writing that X is less than 4 on this interval there, I will substitute this X with my Y over 2 being less than 4. And if I were to multiply this 2 this way, this means what I have here is Y being less than 8. Hence, I have my Y being less than 8 there. Okay? Now we go to the next interval. The next interval here is our X being between 8 and 4. 8 and 4, right? So if our Y is less than 8, it means that the next interval that we're going to have will start at 8, and then we're going to have our less or equal to, and then we have our Y here. Then the third interval will be something that is Y being greater or equal than something, because here as we have our Y just being greater than 8. So also the last interval that we should have there should be Y should be greater than something. And the reason why I left this first part here, I did not complete this first part, is that what we have here actually depends on what we're going to have here. Why? Because remember, Y is equal to 0 here. So there's not much that we know about Y when it's between that, except that it's equal to 0. But we know that when X is greater than 8, our Y is equal to 4X. Our Y is equal to 4X when X is greater than 8. Which means if I were to make X the subject of the formula, I would have that my X is simply just equal to what? To Y over 4. So this means that on my last interval, instead of having X being greater than 8, what I would have is Y over 4 being greater than 8, right? And if I were to multiply, I would have that 4 times 8, which is 32. So what I actually have in fact here is that my Y is greater than 32 at the end. So my y is greater than 32, like that. And then now that I have that information, it makes it easy for me to know that the previous interval should be starting from 8 to 32, like that. Cool. So I took some time to just go through this here because this is also a very important part because it affects whatever we're going to then do here after that. So, okay, I want to write this nicely. So this is our y being between 8 and 32. Cool. So now let's find our CDF. Let's do the final touch-ups to find our final CDF. So what this is telling us is that when x is less than, okay, we don't need to consider this part anymore. So I'm going to quickly wrap this. Now we go back to the statements that we have here. Because now for each interval, you're going to go through everything here. So the first part is saying this is equal to the probability that x is less or equal than the minimum of y over 2 and 4. So the first interval is telling us that y is less than 8. Again, guys, the reason why I was saying it's important for you to be specific whether it's less or equal than 8. This is clearly telling us that don't include the 8. So y is less than 8, meaning y is less or equal than 7. We're looking at number 7 going down. So if y is less than 8, right, which means it can be any number 7 going down. If you were to say 7, for example, divided by 4, or let's say 6 divided by 4, any number that's below 8, you will definitely get something that is less than 8. Do we agree? So in this case here, the minimum is y over 4. So that means that part there is simply just equal to the probability of x being less or equal than, okay, instead of writing this here, I'm just going to write it as the CDF of x evaluated at y over 2. Why? Because this part here, right, is simply just equal to the probability of x being less or equal than y over 2. Again, I'll quickly explain it. This is because, remember, like I said, now we're going to run through this whole statement for each interval, right? Which means we're first going to consider this part, the probability that x is equal to the minimum of y over 2 and 4. And this is saying y is less than 8. So any number that's less than 8, if you divide it by 2, you definitely get something that's less than 4, right? If you take 7 divided by 2, you get like 3.5, which is less than 4. So the minimum here will just be y over 2, right? That's why I have fx, the CDF of x evaluated at y over 2. Why? Because this part here simply gets to this. It gives us this. And this is simply just the CDF of x evaluated at y over 2. Then the next part of this statement is saying the probability of x being between 4 and 8, right? So what this means is that there is no y in this case here. We just want the probability of x being between 8 and 4. So that part will just be your CDF of 8 minus the CDF of 4, right? This is a property, one of the properties of a CDF, that if you want the probability, like we mentioned earlier on, that if you want the probability of x being between A and B, okay, cool. I just got a message in the group that I should repeat something. I'm not sure exactly when the time was, but I'll just try to go back a little bit. So we had this statement here, right? We had this statement, and what we want to do is to translate this information to something that's closer to our final answer of the CDF, right? The first statement here was saying the probability of x being less or equal than the minimum of y over 2 and 4, right? Remember, we are taking, like this whole statement, we are going to go through each term of this. We are going to go through each term and add whatever we get to find a final answer for this part. When we are done, we'll consider when y is between 8 and 32, right? And we consider all the 3 terms. When we are done, we go through each term, but now we're looking at our y being greater than 32. So when y is less than 8, this is saying this is equal to the probability that x is the minimum of y divided by 2 and 4, right? So for any number that's less than 8, if you divide it by 2, you are definitely going to get a number that is less than 4, right? Hence, the answer, if you were to simplify that there, this would just be the probability that x is less or equal than y over 2. Because that will be the minimum. No matter what number you get, the minimum will always be this here. So instead of having this mean part, when y is less than 8, we are just going to have that x will be less or equal than y over 2. Then we continue to the next part there, which says plus the probability that x is between 8 and y. Here, there's not much for us to consider. This is just telling us, okay, you managed to simplify this here. So the next part is for you to then find to add the probability that your x is between 8 and 4. 4 and 8, right? And we know, remember we discussed this property. If x is the probability that x is between a and b is simply just equal to fx of b minus fx of a. This is what I have there. Fx of 8 minus fx of 4, like that. Then the next part then says, this is very important now, guys. Then the next part then says plus the probability that x is less or equal than y over 4 in x being greater than 8. I am going to draw this here. Here, many times you're going to have to actually draw a number line to make, to see for all of this to actually make a lot of sense. So this is the probability of x being less than y over 4 intersecting with x with being greater than 8. So one number that we'll show off here again, like when we're here with a 4, is an 8. So we have 8, that's here, and this is telling us that x is greater than 8. Again, not including the 8, but just greater than 8. So this is something like this, going all this way. But we want this to intersect with some number y over 4, but this x is less than y over 4, which means we have some other number y over 4, but x is now less than that. But we want the intersection, right? Which means we want somewhere where they're going to overlap. But remember, guys, this is a point where y is, we're looking at an interval where y is less than 8. So the first number that we can consider there is a 7. That's the largest number we can consider in this interval, which is 7. So we would have 7 divided by 4, right? 7 divided by 4 is some number 1 comma something. So I'm just going to have 1 comma something here. This is the largest number that we can have. And we are saying x is less than that. So it means our x is just going all this way here. But we also show that our x is greater than 8. And we want an intersection of these two things here. And as you can clearly see, there is no intersection because one number is starting from 9 going onwards. And the reason I'm saying 9 is because we're not including the 8. And the other one is starting from the largest number we can have there as being 7 divided by what? By 4, which we are saying is 1 comma something. So there is definitely no intersection here. As you can see, there is no overlapping. So that is plus 0, right? I am going to repeat this process again for you to understand because even for the next part here, we are going to run through the same thing. But before I go to the next part, can I just get a reaction to make sure that we're on the same page? Also, just with the question that was asked earlier on, I want to make sure if that clarified the question. Can I just get a reaction? Oh, okay, cool. There's just another question here which is asking that why is 7 and not 7.999? Okay, I guess that was me being biased and just using like whole numbers. But definitely you can use also 7.99. But still, if you use 7.99, when you divide that by 4, you will still get a number which is less than way less than 8. So there will still be no intersection. Okay. I hope that makes sense. Now, again, just to go over the question there, oh yeah, it said it's fine. So yeah, whatever number that you divide with there will still not give you an intersection with that. Cool. Let's go to the next interval. Now we are looking at a case where y is between 8 and 32. Again, you would go through each of these statements, right? So this is why everything we did before is very important because whatever we end up having here is what's going to determine what we're going to have as our final CDF here. So the first part here is saying x has to be the minimum between y over 2 and 4, right? So now what we have, I'm going to draw another line. Now our y is between 8 and 4. And again, this part now, guys, this is including. So our y's are starting from 8 and we're going to 32. Now we want the minimum between y over 2 and 4, right? So the minimum number you can get in this interval, let's first consider the part with the y, right? You can get 8, right? That's the number you can start with. 8 divided by 8 will give us, 8 divided by 2 will give us 4, and we have another 4 there. So the minimum number what we have between 4 and 4 is just 4, right? The next number we can get is 9. You say 9 divided by 2, right? You're now going to get 4,5. If you get number 10, 10 divided by 2 will give you a 10. So as you can see now, we're in this interval. whatever number that you put as your y being, right? Because we're looking at numbers 8 and going upwards until 32. Whatever number you put up here will always be a number that is greater than 4. So now in this case, our minimum would then just be 4. Okay, I thought there was a new message. Cool. So now in this case, whatever number we get will just, the minimum will be 4. So that means I'm going to wrap this. I will wrap this now. Before I translate what I have here today, I want to write that this part now here simplifies to just being the probability that x is less or equal than what? Than 4. Because 4 will always be a minimum in this interval, because the least number you can get, again, I'm repeating myself, is 8. And if you say 8 divided by 2, you get a 4. The minimum between 4 and 4 is 4. If you go on upwards, even get towards, because these numbers will always be greater. So the minimum there is 4. And this here, if you can agree with me, this is simply the CDF of x. This is simply the CDF of x evaluated at 4, like that. Then the next part, the next statement there, this is saying we want the probability of x being between 8 and 4. So again, here there's not much that we have to consider. This is simply say, okay, cool, you got whatever answer that you got at the previous term here. Now add the probability. Yes. Cool. So then it says, then now you got whatever you got there. Now add the probability that your x is between 8 and 4. So that's what we're going to do. So this will be plus fx of 8 minus fx of 4, like that. Okay, I hope you can see this, but if you cannot, I'm just going to quickly say it again. So we got whatever we got there, we simplified it to that, and then the next part is like, okay, cool, you have that answer. Now please add that term, and then that term is simply just the probability of f of x of 8 minus fx of 4. Simple as that. The next part then says now also add this term here, which is the probability of an intersection of when x is less than y divided by 4, intersecting with when your x is greater than 8. Again, I will use the number line here. The number that we know for sure there is an 8, right? This is what we have, an 8 there, and we want an intersection, x is greater than 8. Again, not including the 8. Then we are told about this other number x, right? Another random variable x, which is less or equal. This is including. It's less or equal than y divided by 4. The reason why this inclusion there is important is that look at this. Our interval is starting from 8 to 32. So if we were to look at the smaller number, right? If we were to look at the little number, that the first number we can get here is 8. So if we say 8 divided by 4, what do we get? We say 8 divided by 4, we get 2. So this means we have some number 2, which is here, right? And this is included, but our x is less than that. So it's going down like this. So still, as you can see, there is no intersection, right? But you do not only check that number, try and check any other numbers that you can get there. If we took maybe, let's say, I'll take 20, right? Because 20 is between 8 and 32. If I take 20, this means I would have 20 divided by 4, and that will give me a 5, right? So this means I will now have some number, which is 5 here, right? And now these numbers are going backwards like this, including the 5, but I want an intersection, and you can see there's no intersection with numbers that are less than 5 and numbers that are greater than 8. So I can see that all these numbers are not giving me any intersection. So let me go to the largest number that I can get in this interval, which is 32. And now if I say 32 divided by 4, right, that will give me an 8, right? 32 divided by 4 will give me an 8. So finally, now I have a number which is close by, which is an 8, right? An 8 which is here. But the only difference is that now this part here is saying less or equal than 8. So this 8 in this case now is included, right? This is included, which means I'm looking at a case where I'm looking at numbers starting from 8 going this way here. But I want an intersection with x values which are greater than 8, right? But not including the 8, which then tells us that, again here, there is actually no intersection because we are looking at an 8 included and an 8 not included, which means these numbers are actually starting from 9. So again, there is no intersection there. So I have a +0 there. Cool. I hope that makes sense. Then now we go to the last interval. We go to the last interval that we have so that we can finalize this question and move on. Again, we do the same thing. You consider the first part here, which is saying the probability of x being the minimum of y divided by 2 and 4. So now we're looking at any numbers that are greater than 32, and any number greater than 32 divided by 4 divided by 2 would definitely be something that is greater than 4. So the minimum there again would just be the CDF of x evaluated at 4 plus, this says again, add this probability, which is fx of 8 minus fx of 4, right? Plus, now this is where it gets interesting, that in the sense that the last term there wants the probability of an intersection of when x is less than y divided by 4 and when x is greater than 8. Again, one number we are sure of is 8, and we're looking at numbers that are moving from 8 going onwards, right? But now our interval is looking at numbers that are greater than 32, right? And now when you get to this point, now, any number that you can take, when you start from like 31, 32 point, or these numbers here are not including 8, but anything which I've not been saying, I guess, anything that's just above 8, like 8.1, 8.0, or something like that, will be included, which means now when I take any number greater than 32, maybe 32.1 or whatnot, if I then divide it with 4, I'll definitely get an answer which is in this interval there, right? So which means that now in this part here, the way I would simplify this is just something similar as to what I have on top there. What I mean is that what you have there will just be the CDF of y divided by 4 minus the CDF of x evaluated at 8. The reason being is because if I were to simplify this here, before I get this far, I would simplify this here. This part here is actually just, this is the probability that x is less than y over 4, but it's greater than 8. So what I have, this is the probability of 8, and then I have my x like this, and then I have y over 4, like that. But the reason why I have not simplified this earlier on with the term that we're dealing with is because these other two intervals, this is not possible because as you saw, there was no intersection. But now finally there is an intersection, we can write this like this, so that this part here, when we write it down here, this will simplify as just being fx of y divided by 4 minus fx of 8. I'm gonna wrap this and write this clearly. So I'm gonna wrap this now. So what I'm saying is that now when you're looking at the interval, when your x is less than 8, when your x is greater than 32, this now simplifies to just being plus the CDF of x evaluated at y divided by 4 minus the CDF of x evaluated at what was this? 8, like this, right? And if you were to then write your final answer, when you go further to write your final answer, this here, all of this will now just simplify to the following. This will just simplify to having your CDF of x evaluated at y divided by 2 plus the CDF of 8 minus the CDF of x. So CDF of x at 8 of x and y. This is when your y is less than 8, and then you're going to have your CDF. This and there, and this and that will cancel. So all you have the CDF of x evaluated at 8. This is when your y is between 8 and 32. Then this one will cancel with this here. Then the fx at 8 will cancel with that one. So all you'll be left with is fx at y over 4. But this is when your y is greater than 32, right? Then the next step, because of time, I'm quickly just going to leave this one for you. The next step is then for you to go to a CDF of 8 of x, right? Then you're going to plug in y over 2, then plus the CDF of x, you plug in 8, minus the CDF of x, you put in a 4 there. The next part is just the CDF of x, and you put 8, right? So if you were to simplify this part here, this is simply just 1. This is equal to 1 minus e to the power 1 over 2. But where there was this ax, right, you're going to substitute 8. This is the reason why one of the steps that we did earlier on was to find the CDF of x, the one which we got its CDF initially. So this is why it was important for us to get that CDF. Okay. Can I assume that we are all good, guys, so that we can quickly move on to the next thing? Because like I can say time is not on our side here. So I'm gonna try to move a little bit even faster. Cool, can I move on? All right. The next thing that we want to look at, something that I saw in your notes, I'm going to quickly just write it down, which is definitely helpful once in a while, is that if you are given, suppose you're given your PMF, right? I'm going to start to take a situation where you're given your PMF, this is a discrete case, right? You're given your PMF, then you're asked to find the CDF of X, right? The definition that I'm going to give you now is something that you can also use if you need to be sure that it actually works there, is that the CDF of your X will simply be equal to the summation for your n element of your n and your PMF multiplied by your indicator function, and you've got your xn here to infinity of x, like this. What I mean by this definition, what this definition means is that if you're given maybe your PMF of x, right, being equal to, suppose they say it's 1/8 when your x is equal to 0, and it's 1/2 when your x is equal to 1. If I ask you to then find the CDF of x, okay, so there's a question in the group. Oh yeah, yes, you can. Yeah, you can definitely do so. Yes, you can. Okay, cool. So and then the next thing is that this is the formula that you can see in your notes there. The next thing that you have to do, our CDF will be the summation of your PMF multiplied by an indicator function, which is starting from an xn. This xn, this is what your xn is. You have x1 and then your x2, like that. So this is simply just going to be your first probability, which is 1/8, multiplied by an indicator function, which you're going to start with from a 0 here to infinity, and then you put your x like this here, plus you're going to have a half, and now you have your indicator function, and then your x is 1 to infinity, like this. So that's just something that I wanted to say in passing. If you look again in your notes, you'll find that there's this definition that's in your notes there, and it refers back to an example about, I think, tossing some coins 3 times or something like that. It refers back to that, and you can always just try that out to see if this formula will work out for that problem. Again, this is something that you can use if you are definitely sure that you're dealing with a discrete random variable and the PMF of that is given, or maybe you actually need to find the PMF yourself initially. Cool. The next thing is on transformations, right? Still dealing with the univariate case. And now we're just looking at transformations in a univariate case. We'll also look at transformations in the bivariate case today. So I'm gonna try and move a little bit faster. So again, you're given here, we have a random variable x, right? A random variable in a univariate case. But now what we want is a CDF of y, again, like we're doing. We want the CDF of y that we're doing earlier on. And now we are given our y in terms of x. So this is basically the same thing that we were doing earlier on, except that in the previous case, we were maybe not sure whether it's a continuous or discrete, but it's still the same logic that you are given more information about the random variable x, but now you are given this y as a function of your x, and now you want the CDF of your y. So that like now there's actually a more way for you to follow in order for you to actually find the answer to that, right? And this says that when you want to find the CDF of y, here's the process that you kind of follow. This will be equal to, again, using the definition, the probability that y is less or equal than y, right? This is the definition that we know of a CDF, right? What follows is this then, is that now you look at what is your y in this terms of x. Now, because you're given a definition of your y in terms of x. So instead of writing y here, I'll write my g of x being less or equal than y. So this is that step where you would look at the interval and be like, okay, so at this interval, what is my y? But now, instead that we're dealing with just one y, it's not described in interval ways. So instead of just writing the y, I will just say my g of x, like that. Cool. So this will be equal to the probability. You will take the inverse. That is, you make the x the subject of the formula here. Then this will be less or equal than g, like that, the inverse. Okay. Then the next thing, that this is simply just the CDF of your x here, evaluated at this. Again, it might look as more complicated than it looks. but we'll do examples for you to actually just see that it's actually not that difficult. Okay, then the next thing that we do here is in case maybe they ask you to even find the PDF. Let's say the question was then even asking you to find the PDF of Y, or maybe you want to find the expectation of something which will actually might require you to use the PDF if you don't want to use the CDF. The PDF of Y in this case here will simply just be equal to you taking a derivative, right? The derivative of your CDF, the first derivative of your CDF that you would have gotten. Cool. Before we look at an example, I wanted to quickly look at simulation, right? Simulation, or in other words, generating random realizations of some random variable that you have. Suppose we have the random variable x, right? This is the random variable that we are dealing with, and maybe you're asked to find random realizations of this x. All you have to do, right? All you have to do is, okay, you're assuming you are provided with random uniforms, right? You're given some numbers that are randomly uniform, uniform between 0 and 1. Then all you have to do is to say your CDF of x being equal to u, and you solve for x so that you get your x being something like this. I will do an example so that it makes more sense. But all this is saying that when you're talking about simulation, this is something that's definitely going to be in your test, or maybe 3 or 4 marks, where you'll be asked to generate, either say simulate or generate random realizations of the random variable x, right? So what I'm saying is that here you assume that you're given some random numbers which have got a uniform distribution between 0 and 1, and for you to then generate or simulate that random variable, you simply take the CDF, which is the tricky part. Like I mentioned earlier on, the 3 distributions I want you guys to go over. The CDF part, you getting the CDF could be the tricky part in this kind of question on simulations, right? Otherwise, once you get the CDF, all you then have to do is to take your CDF, you equate that to u, and you simply just solve for x. And then when you're done, okay, there's a conclusion that you just have to, it's literally the same words that you always use when you conclude that kind of a question. That is, for let's say you were given, you found your CDF of x to be equal to x over 1 plus x, right? That was your CDF. And the question was asking us to find random realizations of x, or maybe say simulate the random variable x. All you have to do, the first thing, like we said, let your CDF be equal to y. That means I would then have to write 1x over 1 plus x being equal to u. And from that, I just have to solve for my x. And if you were to solve this here, you'd find that your x will be equal to u over 1 minus u, right? And then the conclusion that you always make is that, therefore, given u uniformly distributed between that, well, this statement is saying that if you're given numbers that have a uniform distribution between 0 and 1, then you can put a comma. You can generate random realizations of x by letting your x be equal to u over 1 minus u. So what this is actually just doing is the reason why you equate your fx to u is we want to find a formula of x which we should let x be equal to for us to be able to generate random realizations of x. So remember, this is a random variable x that we're dealing with. So if you just want random numbers from that distribution of x, all you have to do is to let your x be equal to u over 1 minus u, where the u here are just the random numbers which have got a uniform distribution between 0 and 1. Okay, cool. Then there's a quick example that I want us to look at, which is important. It's also a possible 10-mark question that could come. Okay, I'm seeing there's a question in the group. There's a conclusion the other way around. I don't understand that question properly. The conclusion for the other way around.
Exactly how? Could you please type it for me? Is this like in a case where maybe, okay, I actually don't understand. Could you please repeat the question? Okay, cool, sure, thank you. The next thing, I want us to look at this example here, right? Where the example, it says that you're given your PDF of X. So this color is just messed up now. You're given your PDF of X, right? And then this here is defined as follows. That is a quarter, and you've got an indicator function here between 4 minus 4 and 2, X, plus you've got a half, and you've got an indicator function 1 to 2, and X, like this. So the first thing, and what we want here is the CDF of X. That's part A. Part A is simply just saying, find the CDF of your X, okay? Then what you should do is that the first thing you should do always, like I mentioned earlier, whenever you've got an indicator function, try and simplify that distribution into something that will make more sense to us. What I mean by that is that instead of having your PDF described like that here, rather let's have our PDF of X here being in the form that this is equal to half, right? Because what you will simply be doing in this step is to translate what the indicator function is telling you into something that's much easier. This is simply telling us that our PDF is equal to half when your X is between minus 4 and minus 2, like this. Then it goes on further to tell us that our PDF is equal to half when our X is between 1 and our X is between 1 and 2. Right? And this simply just means that when our PDF is from minus 2, right, to this part 1, this means that our PDF is simply just equal to 0 there. So all I've done is that we're given this PDF using indicator function like that. And I've just translated the information to something like this, which is telling us between minus 4 and minus 2, our PDF is a half. Between 1 and 2, it's equal to half, a quarter here and a half here, which means in between here minus 2 to 1, our PDF will be equal to 0. Okay, then the next thing that we have to do, because of time, I'm going to show us, I'll do the first two, then I'll write the final answer for the rest of it, but then it's just simply the same thing that we'll have to do. So for us to get the CDF of X now, right? Remember we gave a definition on how you go about finding the CDF of a random distribution, right? We would integrate from the lower bound. In this case here, our lower bound will be equal to minus 4. So this is us integrating from minus 4 going to X, and what I'm integrating, it's 1 over 4. Why? Because between minus 4 to minus 2, which is what we're considering first here, between those two things, those two numbers, our PDF is equal to 1 over 4. And when you actually integrate that, you would find that our answer will be equal to X plus 4 over 4. That will be our answer there. When X is between minus 4 and minus 2. So my CDF of X, what I have so far is that this is equal to X plus 4 over 4 when my X is between minus 4 and minus 2. Okay, then the next thing we consider when our X is between minus 2 and 1, right? And this is important. I wanted us to get to this part because this is very important. When you're dealing with a PDF, if you're finding a CDF, remember, a CDF is a cumulative distribution function, right? When you're dealing with that and you found the CDF for the first part, like between minus 4 and 2, when you go to the following part, you have to consider what the CDF is in the previous interval evaluated at the lower bound of the second interval, right? This all is true because of the fact that it's a cumulative, so it needs to show some continuation from this interval to that one. But this here only happens if you are moving from a PDF, right? I'll explain why when we're doing a different example as to where you don't add them up.
But whenever you've got a PDF and you want to find the CDF, when you find the CDF of the first part of the interval, when you go to the next one, you will have to evaluate what you got here at what the value of the lower bound of the next interval. What I mean is that for my x when x is between -2 and -1, my f of x here will be equal to, I have x plus 4 over 4 there, but now instead of having an x there, I will write this -2 there where there's x. So I would have a -2 plus 4 over 4 plus, then I will now integrate the usual way that we do for a CDF. I'll now integrate from this -2 all the way to x, but I'll be integrating 0 because between this here, my PDF is equal to 0 with respect to dx. And this here will simply just be equal to -2 plus 4, which is 2 divided by 4, and that's just a half. So this means my CDF between -2 and 1 is just -2 and 1 is just equal to half. So this is -2 and 1. Okay, this is not included there, and x and 1. Okay, so what I just wanted to emphasize the fact that you first have to consider what you got previously, and you have to evaluate that what you got previously at the lower bound of the interval that you would now be considering. Right. Okay, then the next part, I feel like we should just do this here. The next part, again, if I'm looking at the PDF at the CDF between 1 and 2, I have to consider what I got previously, and what I got previously was just a half. So there isn't any x value for me to say I'm going to plug in the lower bound of this here. So I'll just write it as it is. This will be a half, but I'll say plus to do the normal thing that I would do when I want to find a CDF. That is to integrate. So I'll integrate from 1 to x. What am I integrating? This will be half now. Why? Because between 1 and 2, my CDF is simply just equal to half. And when you simplify this here and add that, you'll find that our answer would be equal to half plus x minus 1 over 2. So that means my CDF will be equal to half plus x minus 1 over 2 when my x is between 1 and 2, like that. Okay, but because it's a CDF, one thing you must also just remember, a CDF, as much as you can, you have definitions, okay, of a PDF -4 to -2, -2 to 1, 1 to 2. For a CDF, it's important for us to know that what happens after 2. Right? Unlike here, you can stop when you're just saying between 1 and 2. But for a CDF, we'll be interested in to know what happens after the last number on the last interval, which should always be 1. So in a way, this part here, you can always just write that this when x is greater or equal than 2, this is 1. But for you to show you why it's 1, it's as follows. Again, when you want to find this, we want when x is greater than 2, right? Like I said earlier on, this is a cumulative distribution function, which means you need to start with what you got previously and evaluate it with the lower bound. In this case, our lower bound is 2. We're saying x greater than 2. So what we had there was half plus x minus 1 over 2. And what I'm saying is that we have to evaluate it at the lower bound of the next interval we're looking at, which is x being greater or equal than 2. So the lower bound here is 2, which means when there's an x on my previous definition of the CDF, I will be substituting a 2. So I will have half plus 2 minus 1 over 2, right? Which here is just going to be half plus a half, which will give me 1. But before I write the 1 here, we still have to do what we always do, which is to integrate, right? When we want to find the CDF, integrating from the lower bound, which in this case is 2, going to infinity now. But because there's nothing that we have from the PDF, it should just be a 0 with respect to x. Hence, our answer is simply just going to be the part where we are saying half plus 2 minus 1 over 2, which is 1. This is why the answer there would be 1. But again, this is something that you can confidently just write as just 1 being your answer there. So when you've got all these other parts and hopefully it will be correct, you can simply just write that, okay, so when x is greater than my last bound, which is described in the PDF, my CDF will always be equal to 1. But again, if you have the time, you can always just show your working as to show how you got your answer being 1. Okay, cool. So now what we actually have is the CDF of x there as given here. But the question might not end here because this was not what I wanted us to go through exactly. But I thought it's important for us to find the CDFs because it can be a little bit difficult there. The question there, this is under transformation. The actual question would actually be that now, suppose you're given your y, which is defined as being x squared, right? Now, find the CDF of y. Okay, this is still just under transformations where we are given information about one random variable x, and now we want more information. We want to find the CDF of this one other random variable y. So the first thing that you can note here before we even go any further, okay, firstly, we know that by definition, the CDF of y is simply just equal to the probability of y being less or equal than y, right? And unlike that other scenario where we're looking at where we considered what y is under each interval, now we just know that, okay, y is defined as just being equal to x squared, right? Which means here, instead of writing my y, I can write this thing as the probability that my x squared is less or equal than my y, right? Which means that this is the probability that x is less or equal than plus or minus the square root of y. Again, the reason why we make x the subject of the formula here is because what we actually know more about is x. So we tend to drive it more to what we have more information about, because once we can get what we want, this y, in terms of this x, what we already have, then it's much easier for us to actually get a final answer for the y. So this is what you actually end up having. And this here is simply just telling us that what you want, this x, is between minus the square root of y and the square root of y, which if I were to write it in CDF manner, this is the CDF of y, of the square root of y, minus the CDF of x evaluated this negative square root of y, like this. This is what this translates into. Okay? So now what we need to do now is okay, let me see. What we now need to do is to work with what we have here. We started with the CDF of x, that was our part A. Our y is defined as follows, and now we actually have some formula for the CDF of y. This is telling us that this is equal to the CDF of x evaluated at this minus the CDF of x evaluated at that point. And already we have the CDF of x there. But it only becomes a little bit tricky now in terms of the intervals. Because again, intervals will always determine on whether you get your answer correctly, because they can change everything. Because in this case here, another thing to look at is the fact that y is equal to x squared, right? That on its own, y being equal to x squared, tells us that our y is positive. So whatever interval we're going to be dealing with for our y, it has to be something that is going to be starting from 0, because our y is non-negative. But look at our x there. Our x is starting from -4, which as we can see is negative. So I'm going to quickly wrap this part. Well, I just need more space for what I'm going to do. It involves us drawing some timelines. So I will definitely need some more space. But what we had as our CDF of y, we are being told that this is equal to the CDF of x at the square root of y minus the CDF of x at the square root of negative y, like that, right? So that is what we have. And where did I put my dust? Oh, I made it. So I'm going to wrap this part here. Okay, so here's the trick to how you can approach a question like this here when you get to this point where you've got negatives, but now you definitely know that your y is something that's positive and should be starting at 0 going upwards. So the first thing you can do is to draw your number line. Draw some number line, and this here is the number line of my x values, right? And what I'm going to note is that, okay, my x values are starting from -4, right? From -4. So I'll write my -4 here, and then what follows is a -2. And then for completeness sake, I'm just going to write a -1 as well here. I'll write a 0. And the reason I'm writing a -1 is because on the positive side, you actually have a 1. So try to have all those numbers here. Because I have a 1 here, I'm just also going to include a -1 this side. Then I'll have a 1 here, and I'll have my 2 here. And because again, I have a -4 the other side, I'll also end up at a 4 on this positive side here. Okay, so whatever number I have here, if I have it on one side, I'll also want to have it on the other side. Then the next thing that you need to do is to now consider the definition of your y. We know that y is equal to x squared, right? So if I were to write some interval, let's say between -4 and 2, if I were to write an interval for my y, right, I want to square these numbers. I would say 2 squared and 4 squared, right? 2 minus 2 squared will give me a 4. Okay, this is not writing anymore. Minus 2 squared will give me a 4, right? I will have a 4 here, and then minus 4 squared will give me a 16, okay? And then what follows is I square my minus 2 and my 1 here. Because remember, I just want intervals of my y values now. I have intervals for my x. I know my x is moving from minus 2 to 4, but I know my y is equal to x squared. So I want to see there, what would my y be? So this is what I have here. And then here, what I would have is the 1 and the 4. Why? Because I have minus 1 squared and minus 2 squared. Then here I will have my 0 to 1 because it's 0 squared and 1 squared. I'll have the same thing here. I'll have my 1 to 4, and I'll have my 4 to 16. Okay, so all I've done so far is just I considered what my x values are. Now I just try to make possible intervals for my y based on what I'm told my y is there, as we are told that y is equal to x squared. Now I go into, so I want to write something here. This is my right, this is my left, in a way. I will, yeah, this is my right and left. I'll refer it back to that as to why I wrote that down, okay? Now what follows is for us to actually then write what our CDF of F is, okay? So the first thing you do, remember our Y is positive. So it means our interval is starting from 0. And remember, this is my interval for Y, in a way. I already have my intervals for my Y. So what I do here is that my Y is starting from 0. So this is when my answer will start when my Y is between 0 and 1. My Y is between 0 and 1, which definitely makes sense again, because like we said earlier on, Y is positive. So it only makes sense that it starts from 1 like that, okay? Then the reason I wrote this right and left there, right, is that whenever, if you look at this properly, I have an interval of 0 to 1 here on the negative side. This is my negative side. This is my positive side, right? In a way, this is my left. This is my right. Okay. So what I have here is that I have an interval of 0 to 1 on my negative side, and I also have the same on my right-hand side. Okay. So what you have to do is that the definition of a CDF here is given as fx evaluated at your square root of y, and then the other one at the negative square root of y. So whenever you do this, always start, because for example, if we look at y being between 0 and 1, if you look at this point here, y is between 0 and 1 here and here, then now you need to consider what are the values of x at that point. If we look at the right-hand side first, which is this side, my positive side, I can see that when my y is between 0 and 1, what are my x values? I said my x values are between 0 and 1. So I come here and I look for when x is between 0 and 1. And x is between 0 and 1 when x is between minus 2 to 1. Because this will be minus 2, minus 1, 0 and 1. So my x is between 0 and 1 when my x my y is between 0 and 1 when my x is also between 0 and 1. And my CDF there is half, right? So what I have to do, my right-hand side, right? This is my half there, so I'll take my half, then I have that, minus, you consider the other side now, the other part where your CDF is between 0 and 1, which is this side, right? So you also look at this side now, okay, 0 and 1, what is the value of my x then when my y is between 0 and 1, okay? Then now you just look at it and it shows that it's between 0 and minus 1. And you consider a case where your x is between 0 and minus 1, and that is again here. So this will still just be another minus half, like that, which gives you 0. Okay? I will try and, I know this could be a little bit tricky to understand. I'll explain it again as we do the second interval. So after this now, we have eliminated this part of the intervals, the 0 to 1 and the 0 to 1. What follows, as we can see, is when our y is between 1 and 4, 1 and 4. And as you can see, this is again on both sides. So our y is between 1 and 4. Y is between 1 and 4, like this. Again, you start with the right-hand side. Because as you can see, 1 and 4 is here as well. 1 and 4 is also here. But you always start with the right side. So whatever you establish should be a CDF for this one, then you will substitute this right-hand side on that. Minus whatever you establish your CDF to be on this side here, is what you're going to substitute your minus negative square root of y there. What I mean is that for when my y is between 1 and 4, I consider the right-hand side first, which is here. Then I look at, okay, when my y is between 1 and 4 on the right-hand side, what are my x values? And I said my x is between 1 and 2. Then I will come to this CDF of x, and I say, okay, sure, when my x is between 1 and 2 here, my CDF is equal to 1/2 plus x minus 1 over 2. So I will take that, the right-hand side, and that will be half plus. But instead of writing x now, what I will write is square root of y. I will explain why is square root of y. This is something I should have written earlier on. Now, because my y is equal to x squared, right? This means my x is just equal to the square root of y. Okay, and the reason why I am writing in terms of my y now is because remember we want the CDF of x. So whatever we have as our final answer should be something that is just in terms of my y. Again, just to go back to what I've done, I'm looking at my y between 1 and 4, and then this is what I have. I found what my x values are for when my y is between 1 and 4 on the right hand side, which is 1 and 2. I found the CDF, and this is what I wrote down here. But instead of writing x, I wrote the square root of y because this is what x is equal to, right? Then remember, this is saying that the CDF of y is going to be that, the right-hand side, which is what we have covered now, minus, so I'm going to have a minus sign here. The CDF of x is evaluated in that part now. So for this term, we're going to look at the negative side now, the left-hand side. And we'll look at our y between 1 and 4, and then we consider what x values we have, right, on this side. And this is when your x is between minus 2 and minus 1. And minus 2 and minus 1 is here in that term. And the CDF of x in this case now is simply just a half. So what I would have here is just minus half, and this and that would cancel. And the answer I would get is just the square root of y minus 1 over 2. That would be my answer in that case then. Okay, you go on forward, right? The next interval that we have is that of x being between 4 and 16. So now I have my y, sorry, not x. My y is between 4 and 16, like this. So again, you consider, because remember we have 2, 4 to 16, this one and that one. You consider the right-hand side first, and when my y is between 4 and 16, what are my x values? My x values are between 2 and 4. Now you go to your CDF. What is the CDF when your x is between 2 and 4? And here it's given that whenever your x is greater or equal than 2, our CDF is equal to 1. So I'll take what that CDF is there, which is 1, minus x by the definition. I will then consider on my left-hand side, which is my negative side, when my y is between 4 and 16, what are my values of x? And you find that your x here is actually just between minus 4 and minus 2, right? Which is this part of the interval, right? So I'll have a minus there, and then that means I have to write that CDF. But instead of writing x there, what I would write is the negative square root of y. So what I actually then have is 1 minus the negative square root of y plus 4 over 4, like this. And if you were to simplify that, you find that your answer would be the square root of y over 4, like that. And again, remember, if it's a CDF, right, we want to know what happens after the last bound that you have. That is, we want to know what happens when y is greater than 16. If you do, this is just a way to actually check for yourself if you understand what exactly I was trying to do here. If you do the same thing that we've done for all this year, you'll find that when y is greater than 16, which we know should be the case now, this should just be 1. So if you follow the same process that we've been doing, that you consider, except that now when x is greater, when y is greater than 16, in this case here, it means our x is greater than 2 and 4, going that way. You just have to consider that part there. Otherwise, you find that the answer that you get there should just give you a 1. Okay? We are very much behind time. Oh yeah, okay, there's a question. Oh, okay, no. I think I took that for granted for a bit there. The inequalities are not. So that, like in this case, it was not very important since we know our distributions, but this should just be between that and that. And okay, I don't even have the question now. Let's see. Oh yeah, can you just guys fix the inequalities from what we had initially? This I think should have been between this and then that. Okay, where else can I start? This is greater than. I think it was something like that, yeah, but can you fix it? It's just that unfortunately, in this case here, our inequalities don't really matter because they're not evaluating at any point, but yeah. Can you just double check from when we started the question? Okay. I'm just writing something in the chat group here, guys. I'm still here, don't worry. Okay, what I was just saying in the group there, in case it doesn't really make sense, that in this case, fortunately, it doesn't really matter, but just to be safe, whenever you are given inequalities from the beginning of the question, just keep them as they are as you go forward. Okay, I hope that this question was fine. It's something that you definitely have to be comfortable with answering, because if you were to look at even like past OTs from maybe other years, you'll find a question like this, and I think there are like 2 or 3 kind of questions like this that you would find. And another question, remember when we were starting, we spoke about absolutely continuous random variables. This is the kind of a question where the follow-up question could then be asking you if X is if Y, I mean, is absolutely continuous, right? And if you were able to find a CDF like this, right, for you to conclude such a question, this is how you would do it. After finding this, you would start by saying yes, right? The fact that you were able to find this CDF that we did here, your first, when you answer the question, the conclusion will be yes, it's continuous, right? And this is your reason, because you write yes, it's continuous, because the CDF of Y evaluated at B minus the CDF of A, right, is equal to you integrating between A and B, the PDF of Y is with respect to Y, where, so this is the only tricky part now, where your F of Y is equal to, then you write that down. So in you answering the question on whether your CDF of Y, your random variable Y is absolutely continuous, all you have to do, given that you were able to find the CDF here, right? This is all you need, firstly, right? So your answer will be yes, Y is absolutely continuous. Why? Because the CDF of Y evaluated at B minus the CDF of Y evaluated at A is simply equal to you integrating the PDF of Y between A and B, where your Y is. So the only part where you actually have absolutely continuous or not, all you have to do to write is this statement there. When you're done with the statement, then you find your PDF of your Y and write that down. Okay, I'm going to move on, guys, to expectation and moments. Now, can I just get some reaction to be sure that we are all still moving together? Okay, cool. Awesome, guys. I'm glad to know that you're still with me. And then let's continue. The next part is expectations and moments. The first one is just the simple definition of what we know expectation to be from first year. Right? So I'm going to quickly write this down fast, just for the sake of completeness. But we know that the expectation of X, right, is either equal to us summing across X multiplied by the PMF of X, right? This is in a discrete case. And then we also know that this could just be equal to us integrating over the whole interval of X multiplied by the PDF of X, and then this is with respect to X, right? And obviously, this is a case where our x is what? Our random variable x is continuous. Cool. What follows is the law of the unconscious statistician, right? Which tells us that if you want to find the expectation of something which is in terms of x, right? Again, this falls under when you're doing like some sort of transformations that you have a random variable x, but now you want to find something else that is written in terms of x. You want to find its expectation. This will simply just be equal to you integrating, if this is continuous, you integrating over the whole interval. What are you integrating? It will be that function that you have is in terms of x multiplied by the PDF of x with respect to x. This is obviously in a continuous case, which means that if you're dealing with a discrete case, you will simply just be summing over across x, g of x multiplied by f of x, d, no need for a dx here. And just to bring this into, for it to make more sense, this whole law of the unconscious statistician is that maybe you were given a random variable x, maybe it's exponentially distributed with lambda, right? And then now you're asked to find the expectation of 1 over x, right? If you look at this closely, this is definitely not x. As you can see, what we have information about is x, not 1 over x. This is some other function just in terms of x that we have now. So for you to be able to find the expectation of this here, what you have to do is to integrate, right? Because x is exponentially distributed here, you would integrate across 0 to infinity. What are you integrating? Your g of x. This 1 over x is in this case our g of x. So what you're integrating will be 1 over x multiplied by the PDF of x dx. Like this. This is something that I think is quite simple, but I just thought we should definitely just look at it. And another thing which is very important, which we will use more when we're looking at conditionals than now, is our dat Vader. Right, the dat Vader method. This is still just a method for us to find expectation. But what makes it easy is that there are cases where, because what we're doing now, the definitions we just looked through now, and in first year, was when you are sure that the random variable that you're dealing with is either discrete or is continuous. But there are cases where you would not be sure, right, whether it's discrete or it's continuous. But for the moment you know that it's non-negative, right? The moment you know that the random variable you actually have is non-negative, then you can apply dat Vader, the dat Vader law, which says that the expectation of x will simply be equal to you integrating from 0 to infinity. Again, this 0 to infinity comes from the fact that the condition for us to apply the dat Vader method is that your random variable is non-negative, which means it's starting from 0, whatever it's going to end to, but the lower bound is 0. But when you find the expectation, you will integrate from 0 to infinity. But now what you're going to be integrating over the probability that x is greater than x, and this is done with respect to x, right? Where this is simply just your survival function, which you say is equal to 1 minus your CDF of x, right? And I will quickly just write this down. This is probably an easiest thing you would get, but just to make sure that this makes sense, right? If you're given your CDF, suppose your CDF of z that you're given here is equal to 0, where your z is between 0 and 1, and it's equal to z 1 plus z when your z is greater than 1, right? If you're asked to find the CDF of z in this case, you can definitely apply your dat Vader, because as you can see, z is starting from 0 and it's going upwards, so it's non-negative. Like, you obviously can use other methods in this case, but I'm saying in a case where you feel more comfortable to apply the dat Vader method, because you also need to look at what's faster. In this case here, if you wanted to use maybe other methods like from first year, it means you first need to find your PDF, and then when you find the PDF, you integrate while multiplying with x. But if you're going to use the dat Vader, you already have your CDF, so you can quickly get your survival function. Right? Anyway, my point was that with this example is that whenever you're given a CDF like this here, when you're given this 0, you need not to take that for granted, because I've seen a mistake that I've also made before, is that when you now consider your survival function, you can easily just ignore this part. Why? Because it's 0, and you just say that your expectation of x will be equal to you integrating from, let's say, 0 to infinity of 1 minus z over 1 plus z, right? This will be wrong. Why? Because as much as your CDF is 0 when z is between 0 and 1. Okay, cool. There's a question here which is asking if that is only for continuous. Okay, I guess I should have also done this here. X. This can definitely happen. You can definitely do that as well, right? Yeah, you can definitely do that. But then let's see. Hold on a second. No. You know what? Okay, I would have to confirm this, but I'm not sure about this because the moment we do this, right? The moment we start using summations and whatnot, it means we are differentiating between discrete and continuous. So for now, I will confirm this, but for now, I think this is what we have because this is saying whether we don't know whether it's discrete or continuous, but the condition is just that if your random variable there is non-negative, then you use that, right? Because once we start summing, it means we were able to say, okay, this is discrete. Because once you're summing like this now, summing will just be like 1, 2, 3, like that. So this now means that you're saying the random variable is is discrete. So for now, when you're applying our that Veda, let's just keep it with this definition for now, right? Which says that if your random variable is just non-negative, right? It doesn't matter whether it's continuous or discrete. This is how you find your expectation. Okay, cool. And then, so what I was saying is that if you were to find your expectation now, the expectation of x, in this case, this will be equal to, and the reason I was saying you should not ignore this part which is saying 0. Remember, our survival function, which is what we integrate when we're using that data, says it's equal to 1 minus the CDF of x, right? Which means this will be equal to us integrating from 0 to 1 for starters, 1 minus the CDF, where the CDF is 0 there. So this will be 1 minus 0. So there's actually something that is happening here now when I'm using that Veda. Even though the CDF is equal to 0, the survival function is not equal to 0 in that case, right? So this is with respect to our Z plus integrating from 1 going to what? To infinity of 1 minus Z, 1 plus Z with respect to dz. Again, now this part is just now you're doing some math. But what I wanted to emphasize is the fact that whenever you're given a CDF and there's a 0 somewhere there, do not take it for granted because if you're going to use that Veda, which uses your survival function, it will not always be 0. It might probably be, it will definitely not be 0 to be 1 wherever your CDF was equal to 0. And can I just confirm with you guys that we are all good? Before I confirm, before I go on forward. Can I get some reactions? I just got 1, I've got 2, 3, and the last one. Okay, okay, cool. So anyway, this year, like I said, I will confirm this, but for now, I think from what I know from my knowledge, this is what I've always done, and I think that's it. I'll confirm that. I'll go back to that. And the next thing I want us to look at are moments. Yes, our moments. So now we've kind of have a feel of what these expectations and whatnot are. Now we're going to look at the moments. And guys, looking at the time now, we might slightly just go over above time. But I'll try to be as quick as possible so that whatever time we're going to take there will not be too much. And for moments, the first thing, our uncentered moments, right? Because remember, we've got centered and we've got uncentered moments. Then the uncentered ones, right? I'm just going to write moments here. Our uncentered moments, right? The expectation of XR here, like this. We will use the law of the uncontested statistician. Because again, we might have information about X already, but now we want the information, we want the expectation of X to the power R, which is some other function just in terms of X. So in a discrete case, this will simply be the summation. This will be a summation of XR multiplied by the PMF of X. In a continuous case, we're integrating from minus infinity to infinity. What are we integrating is XR multiplied by F of X dx, like this, right? In a case where we're dealing with the centered moments now, right? Centered means we're looking at the expectation of this random variable x minus the mean of that random variable x, or to the power r, like this. These are our standard moments, right? Which we know that when r is equal to 2, for example, when r is equal to 2, that will be our variance. We get our variance of x, because all we have is the expectation of x minus mu x all squared, right? And from that, we even go forward to define other important properties about random variables, right? That is skewness and ketosis, right? So for our skewness, the coefficient of our skewness, as we know, this will be equal to the expectation of x minus the mean of that x all cubed divided by this here to the power 3. And then our ketosis, this is something anyway that you will find in your notes. The ketosis will be the expectation of x minus mu to the x all to the power 4, and then divided by this here, but now to the power 4, like this. So this is just definitions. We'll put these definitions into use so that it makes more sense than just looking at it as it is on the board like that. And another thing which is under this chapter that we will not use today, we'll definitely use it tomorrow when we're looking at convergence and whatnot. And this is Chebyshev's inequality, right? This is Chebyshev's inequality. Chebyshev's inequality. And Chebyshev's inequality, I hope you can see this, my markers are drying out. The Chebyshev's inequality simply just tells us that if you want the probability, oh my God, it tells us that if you want the probability that x minus its mean, right, is greater than some k, this is simply less or equal than the variance of that x over k squared. This is something we'll be using later on when we are proving convergence in maybe probability or something like that. Well, what the inequality just tells us that you've got a random variable x, and obviously, like what we've been doing now, we know that if you've got a random variable, we can find its properties, including the mean. So what this is saying that the probability that the distance between x and its mean being greater than some k, which is a positive number, is always less or equal than the variance of that random variable divided by what you want it to be greater than squared. Again, this is something that we're going to look more into depth in tomorrow when we, not tomorrow, man, in the next workshop where we will be looking at convergence of random variables to some number. Okay, now I have this quick example that I want us to go through on this, on moments, right? So suppose you are given a random a PDF of x like this. X is equal to 5 divided by x to the power 6. By x to the power 6. X to the power 6 like this. That's our PDF of x, right? And then the next thing that could be asked is that maybe find the skewness, right? I'll find the skewness here, but finding the ketosis is just the same thing, except that now your arc moment, on your uncentered arc moment, your R will be equal to 4. But if you wanted to find the skewness, let's say here what we're interested is that the skewness. And then, so obviously we know from the skewness, we will need the arc standard moment when we simplify it. The numerator of the skewness is the expectation of x minus the mean of x all to the power 3, like this, right? And earlier on, when I was talking about some things that you will need to go over just to make things easier for yourself, was the Pascal's triangles, right? And Pascal's triangles will tell you that when you simplify this or expand it, if I can say, is this will give you the expectation of x to the power 3 minus 3 mu x multiplied by the expectation of x squared plus 3 mu squared expectation of x minus the expectation of x all to the power 3, right? If you were to use Pascal's triangles, you would find that if you expand this, this is what you get. So can you please quickly can you go over like Pascal's triangles and get familiar with that again? Because whenever you need to find the skewness and ketosis, one or the other, you will need to be able to know how to expand this here. Because that can also go to being to the power 4, right? And as you can see that even though we had the unstandard earth moment, this will lead us to the earth moments, right? Which means we need to know what our earth moments are. And by definition, we know that this here, the expectation of r of x to the power r of x to the power r, as it looks like there, except that now our r can be 3, can be 2, can be 1, like that. We know by definition, or even by the law of the unconscious statistician, right, that this here will simply be then will be equal to, our x here is greater or equal than 1. But that's the information that you're given the PDF, and x is greater or equal than 1. And then we will get that our arc moment will be equal to us integrating from 1 up to what? To infinity, right? What are we integrating? We'll be integrating x to the power r, which is what we have there as our function, right? This is equal to x to the power r multiplied by what? By the PDF that we have here, which is 5 over x, which is 5x to the power 6, like that. Then this is with respect to our x, right? So what I have here is x to the power r multiplied by 5 divided by x to the power 6, right? And this is just math there because you're going to take the 5 out and you're going to have x over r divided by 6, which you can write as x to the power r minus 6. And if you do this properly, you would get that this is 5 integrating 1 to infinity, your x r minus 6 dx, and your answer here should give you 5 over 5 minus r, right? That is your answer that you would get there. And so this is telling us that expectation of x to the power r is simply just equal to that, which means that if I were to continue there, the expectation of x to the power 3 is simply just equal to, my r is equal to 3, which means this will be equal to 5 over 5 minus 3, which is equal to 5 over 2, like that, right? That's what that means there. So because of time, I'm just going to trust you guys that you can finish the rest of the terms there. Because this just means that the next term, this expectation of x squared, right? This means my r is equal to 3. All I will just have now is 5 over 5 minus 2, like that. The only thing that you're going to have to work on now is your mu of x. But working on it means you just need to find the expectation of x. Well, this is the expectation of x. And you finding the expectation of x here is just going to be you integrating x multiplied by f of x, right? You find the expectation of x the normal way we did last year, and as we defined expectation earlier on. Unless if you've got the will and time to find the CDF and also use that data. But for the expectation of x, you actually just need to find it, right? But the nice thing is that with questions like this, you could even get a simple distribution, like an exponential distribution, whose expectation will be easy for you to find. So you may not need to do that. But in a case where you've got a PDF like this, you will need to find your expectation the normal way. And for our numerator, for denominator for the skewness, right, where we need your variance, right? Remember, you must always just use this definition of variance. That your variance is equal to x minus the mu of x all squared, right? And all here, all what this is simply just, there's a question. Even better, okay. There's a question in the group there to even save the time. I don't know, I complicated things here. You can simply just let your r equal to 1. Because remember, expectation of x is just expectation of x. So if your r is equal to 1, you find the expectation, yeah. So that's all you just need to do there. You let your r equal to 1 and you find the expectation. Definitely much easier and faster, and will save you a lot of time. Okay, cool. And then for your variance, just remember that your variance is simply just your unstandard earth moment when your r is equal to 2, right? So you could even just use your, what do you call this? You could use your Pascal triangle again to expand this, and you will use your earth moments to find your answer for your variance. Or if you do not want to do that, we also know that your variance your variance is simply equal to, your variance of x is equal to the expectation of x squared minus the expectation of x, like this, all squared, like that. So instead of you using the arc moment to find that, the unstandard one, you can then just do this, and we know that this here you can get from that, and then also this year expectation of x would have gotten it by letting your r equal to 1, and that's just being equal to whatever you get there. So you can always use that to find your variance, right? And then there's something that I would like you guys also watch out for when you're doing these kind of questions, right? The best case that you can get when you are finding your skewness and your ketosis, right, is if the distribution you're dealing with is your exponential distribution. And this is the reason why it's the easiest when you're dealing with this. Let's say you're given a distribution with exponential and your lambda is equal to 1, right? And if you want your arc moment, x to the power r, like that, we now know that this is simply just equal to us integrating, right? This will require integrating. Exponential distribution is positive from 0 going to infinity. So this will have us integrating from 0 to infinity. What are we integrating? It's x to the power r multiplied by the PDF. And then in this case here, our PDF will be e to the power minus x dx, right? And this is definitely something similar to what we've seen before when we're looking at the gamma distribution. Remember that our gamma distribution, we had this here, which was equal to 0 to infinity, and we had t to the power x minus 1, and it was e to the power minus t dt, right? I don't know if I wrote this, but even if you check in your notes, this here will simplify to being equal to x minus 1 factorial, right? Where is x minus 1 coming from? X minus 1 is simply the power of t in this case. You look at what you're saying, t to the power 2, and then that will simply just be equal to x minus 1 factorial. So it means when I want the arc moment for the exponential distribution like this, this is simply, it's similar to what we have here, except that now our numerator is r. So this means that this here can simply just be simplified to being r factorial, which means when you expand your definition of your numerator of your ketosis, for example, or your skewness, where you will have x to the power, where you have the expectation, of x to the power r, this will simply just be r factorial. That is where you want to find the expectation of x being to the power 3, this will be equal to 3 factorial, like that. That's what you would have there as just being 3 factorial. Again, I was just saying this in passing that when you need to find such properties of a random variable, whenever they're given exponential distribution, and even better, your lambda is equal to 1, just look out for a case where you will just have to do this here to simplify your answer for yourself, so that you won't have to waste time trying to integrate. And again, this is something that you can really expect, because if you're given something that's much more difficult, you would want you to worry less about finding an arc moment, and that's the best way that you can make it as easy as possible for you. If it doesn't give it to you literally, you would give it in this manner where there's just a small trick that you need to apply for you to be able to get to the answer that you need. So please do watch out for the exponential distribution when you're finding this here. Cool. Now we are going to look at the first bit of our bivariate cases, right? That's the first bit of it, and random vectors. So now initially for the past 2 hours, 30 minutes, we're dealing with a case where we just have the random variable x on its own. Now we're going to be dealing with a vector. Now we'll be dealing with a vector which is made up of our x and y, right? So we're dealing with 2 random variables in this case now. And we can also still find properties of this. The same way we're finding properties of just x on its own. We can start by even finding the CDF. We are able to find the CDF of our z, right? and this will be defined as, in a case, okay, we can also write this as being equal to, I'm holding too many papers, so the CDF of x can be written as follows. Instead of writing the z there, I can write this as fx, and I'll write my xy here, and I have my xy like this. So finding the CDF, if it's a discrete case, I can simply sum over both x and y. What will I be summing will be my joint PMF of my x and y. Then if it's in a continuous case, that I will be dealing with, I will do my double integration from the lower bound minus infinity, also for this one to minus infinity, to y and to x. And what will I be integrating? It will be a joint PMF of my x and y, like this. So basically, like we were doing earlier on for a univariate case, you can also then just find the CDF of your z, your random vector of x and y, in this manner. Again, this might look more complicated than it is when you're looking at it like this, but when you put this into practice, we'll find that this is actually quite easy. Then the next thing we will look at is considering a probability. You could ask the question whether, like, find the probability that x and y are an element of some region D. This will simply just be equal to a double integration with respect to that D region. And what are you integrating? It's your joint PDF of x and y, and this is with respect to your x and with your respect to y. Keeping in mind that here, it's up to you whether you want to start by integrating with respect to x or with respect to y. Okay, and I would again consider an example where we actually use this here. Then the next thing that we know is that as much as we have the random vector z with x and y, there are cases where we would want to, we're more interested in what x is on its own or y is on its own. So we need to be able to extract information about x or information about y from that vector that we have z. And what I mean is that if you have the joined, PDF of your x and y, you can find the marginal of x, right? The marginal of x, and you'd find this by integrating from minus infinity to infinity. You'll be integrating the joint PMF, but if you want for x, you will do this with respect to y. Similarly for y, you would integrate minus infinity to infinity your PDF, but you do this with respect to x in this case. And this is not something that you can only do for a continuous case. You can definitely do this as well for a discrete case, where now in a discrete case, you will be, for you to find the PMF of your x here, this would involve you summing, right, your joint PMF of x and y. But if you want for x, you do this with respect to y. And if you want for your y, you will do your summation with respect to x like this. Okay, this is again just some simple notes that you find in your notes. The next thing that's important is about independence, right? So this goes both ways, that if x and y are independent, then this follows that the joint PDF of x and y will be equal to the product of the two marginals as we have there. Again, this is not only for a continuous case, even for a discrete case. If x and y are independent, then the joint PMF of your x and y is still equal to the product of the marginal PMFs of your x and your y, as I've written there. Okay. The next thing that's important, remember, we specifically paid attention to the uniform distribution when we're dealing with the univariate case, right? Let's suppose you are given your x and y that they have for a uniform distribution, right? And they are uniformly distributed. Oh, there's a question. Oh, how would you find, the question here is, how would you find your PDF if it's not independent? The joint if it's not independent. Because in this case, I had said if they were independent and you've got the marginals, if you want to find the joint, you can simply just multiply the two things. I guess I did not mention that if you actually have the joint CDF, right? If you have the joint CDF of your X and Y like this, right? The same way if you had the joint, if you had the CDF of X, if you wanted the PMF of your, if you had the CDF of X, if you wanted the PDF of X, you could just do that by finding the first derivative of your CDF. Even in this case as well, if you've got your CDF of X and Y, if you want the PDF of your X and Y, you can simply just find this by taking, this is how you do it. If you want the joint PDF of X and Y, right, you can find this by taking the derivative. But now, because we're dealing with two random variables, you will not take the first derivative, but you do this twice. You take the derivative twice of your CDF of X and Y, and you can first start this with respect to X, and then you also take with respect to Y. That will give you your joint PDF. Let me just quickly go over that again. If you want the PDF of X and Y, right, either maybe you'll be given information about your X, your marginals, right, and if they're independent, you simply multiply the two marginals and you find your answer. But in a case where you're not given that they're independent or whatnot, you can find the CDF, because earlier on, like here we have this here, we know the definition, we know how to find the CDF of a random vector. So you can either then start by finding the CDF of your X and Y, and once you have that, instead of just finding the first derivative like we did in a univariate case where you've got the CDF of X, and if you want the PDF of your X, you take the first derivative. Now you take the derivative twice, but you do this in this manner, that you first find the derivative with respect to X, then when you find the answer, that answer you take the derivative now with respect to Y. The answer you get there should be your PDF of your X and your Y. Cool. I hope that answers the question. And if we're looking at the uniform distribution, like I was about to talk about, remember in a univariate case, we said you could have a random variable X, which has got a uniform distribution between some interval, and for you to find the PDF of that, all you had to do was to say 1 over the length. Now, in this case, we would be told that you've got your X and Y, and this X and Y here are uniformly distributed between a region now, a region D. For you to find the PDF of your X and Y now, this will simply be equal to C if your X and Y are an element of that region, and it's zero otherwise, all right? And I'm going to define this C. Your PDF will be equal to C if your X and Y are an element of that region, where this C that I've written here will be equal to, where this C is simply equal to 1 over the area of D, right? And the perfect example that I had to explain this was a bivariate case where you've got your X and Y are uniformly distributed, and the region D was described as follows: that your Y was between X, your X was between 0 and Y, and your Y was between 0 and 1, like this. So this is the information that you have, that okay, you've got this random variables, this bivariate case, a random vector Z with X and Y, and they are uniformly distributed in this region here, right? So this means you need to draw this region, right? You will need to draw this. We know our Y is between 0 and 1, so I can have a 1 somewhere here, and I know my X is between 0 and Y, which means I have the function Y is equal to X. I will draw it here, but this is the case where Y is greater than X, and Y will always be greater than X on this top part, and X will always be greater than Y at this bottom part here. So here, your Y is greater than X, and here, your X is greater than Y. Why is that the reason? This is because if I'm considering this case here, this part here, right? My Y is equal to 0 here, but I can move forward here, my X will be increasing, but my Y will still just be 0, which means all the numbers that I will have going upwards here, my X will always be greater than my Y. Why? Because my Y is 0. But in this case here, my X is 0, and as I go up there, my Y will be increasing, going to infinity, and my X will be still 0. So that's why your y will always be greater in this region on the top side, and your x is greater down here. Okay, there's an answer. Yes, I think it's safe to say so. Because I just answered the question there because I don't know how far you guys had gone to with LA, but I'm sure by now you'd have looked at vectors. Because remember, your x and y here is actually just coming from what we said is a vector z, and this vector here contains our x and y. Cool. So what we now have is that our region is defined as our x being between 0 and y, right? So this means our y is greater and our y is between 0 and 1, which means the region that we are considering is actually just something which is here. So if we want to find our joint PDF of x and y in this case now, which you said is going to see if x is an element of the region D. So this is the region that we have here. And we said where C is equal to 1 over the area of D. And as you can see there, that region that I've shaded, our D in this case, is simply just a triangle, which means our C is equal to 1 over the area of a triangle, right? And we know an area of a triangle is half times base times the height, which this is 1. And because this is the line x equal to y, it means they are all equal. It means at this point here, my x is also equal to 1. So my height and my base are both equal to 1. That's my area. It will be equal to 1 over 2 times 1 times 1, which is just my half, right? So my PDF, my joint PDF of x and y in this uniform case is simply just equal to 1 over my area, which is half. So my answer would be 2, like that. And in a uniform case, there is this thing, if they wanted you to find maybe the marginals of x and your y now, it's just you integrating this half. If you want the margin of x, you'll be integrating your half, but with respect to y. If you want the marginal of y, you'll be integrating your half, which is a joint PDF, but now with respect to x. It's just the other way around. So I just wanted to emphasize on that part about a uniform bivariate case, because it's quite an important thing to do. And in most cases, if you are dealing with a uniform, it's either going to be on an interval, right, in the univariate case, where the area will be quite simple. And then in a case where, in the bivariate case here, the area you'll be looking at, it will be either maybe a triangle, as we said in this case, or maybe for sometimes it could come around trapezium. So just look at how to find the area of a trapezium that you are showing in case it comes up. Or one case that's very popular is a circle. Then you need to find your area as just being the area of a circle. Cool. Again, the same way we had transformations in a univariate case, we can also have transformations in the bivariate case, right? In the sense that we would first start with your random vector G, right? With your random variables X and Y. And then now later on, you're told that there's this other vector, right? Which has got X and Y. It's on some other function, but in terms of X and Y, okay, let me not write G here. I want to write H, because this will be something different, something like this. And you also have V, okay? Okay, I can even write G like this here, X, Y, like this. So you could have a case where you have these two things, and you've got your U being equal to that, and you've got V being equal to that, and you have to find, let's say, maybe the joint PDF of your U and your V, right? So that's what you'll be actually dealing with when you're looking at transformations under the bivariate case, okay? Now, there are two ways in which you can do this. I'm going to quickly look at those two ways. The first one is that the first way to deal with such cases is that maybe you are given a random vector, right? You've got your X and Y like that. And then they ask you to find a CDF of Z. Let's say you're told that maybe your Z is equal to X plus Y. So what actually happened here is that you've got your X and you've got your y separately, then they say suppose you've got a random variable z is equal to x plus y. There are two ways in which you can answer a question like this here. The first way is the basic way, right? Which says that if you want the CDF, use the definition of a CDF. The CDF of Z, right? By definition, a CDF is simply just equal to the probability that Z is less than the small letter z, right? Where remember the small letters, like I said earlier on, this is just some constant that you have somewhere there, okay? Then this here will be equal to the probability that instead of writing Z now, remember there's this transformation that Z is actually equal to x plus y. So instead of writing my Z, I will have x plus y being less or equal than Z, like this. This is what I have, right? So from there, this comes back to, remember when we had this formula which was saying the probability that your x and y are an element of some region D, and you have to do like double integration to find what that is. That's exactly what you would have to do in a case like this here, right? Where the only thing you would, okay, I will do an example later on. Just now, I just want to quickly get through the small theory part of this, so that I will do an example on how you would solve a question like this here. But basically, what this will involve is you drawing. You will come up with a line, because you need a region. You will come up with a line here. You will take this as it is inside. Actually, let me just cover it. That is your x plus your y being equal to this small letter z, right? You make y the subject of the formula. So now I have z minus x. Then all you have to do now is to draw the region. To draw the line, I mean, you draw the line y is equal to z minus x, where you find the x, you find the y-intercept. Your y-intercept is when x is 0, so you have a z here. Your x-intercept, your x will be 0, and you find a z. So all you would have actually is a line like this, and it's saying less than z. So less than z, less than z. So what I actually have here is that region there. Then what will follow is you doing double integration, because remember, this was the definition of the probability that x was xy when element of some region D was equal to a double integration on some region D, and what you're integrating is the joint PDF with respect to x, with respect to y, depending on what you want there, okay? So now, this is what I'll just be doing here. This is assuming obviously that you were given extra information about your x and y, maybe that they are independent, exponential, so you're able to find their joint PDF by simply multiplying the marginals to get your joint PDF, or maybe you were literally just given that, okay, here is the joint PDF of your x and y. Then now what would follow from there is that this would be equal to you integrating the joint PDF of your x and y. Now, this is something that when I said go over double integration, you can also look at. Now, when you're deciding whether you want to, which one you're going to integrate with respect to first, it's always best that one of them be moving from 0 to another constant, right? In this case, there is a constant, because you find that if I were to look at x, for example, consider x, if I draw a line like this is saying my x is moving from 0 to this line, right? So I want to integrate with respect to x first. So this will be moving from 0 to this line. What is this line? This is my line y is equal to z minus x, right? But because I am integrating with respect to x, I will not want anything in terms of x as my bound. So instead, I will write this here as being x being equal to z minus y. So my integration will be coming for, in terms of x, with respect to x, we'll be starting from 0 here, all right, 0, going this way to this line, which this is a line y is equal to z minus x. But like we said now, we don't want to write this in terms of x because we're integrating with respect to x. So I will have z minus y. And like I was saying, it's always best because in most cases, when you look at a probability like this, a probability case like that, you want a number, a constant. So it's always best for you to then have a bound which is at the outer is just in terms of constants, so that you can have an end value in terms of a numerical value, right? So if you were to look at y in this case, y will be moving from 0 going this way to my z. So this will be 0 going all the way to z. Because remember, in this case here, this z that I'm using now is a small number, it's a small z, it's a constant, right? Hence I am saying my outer bound now will be moving from that to z, like that. So that will be then what you will have to integrate between to find your final answer. Like that. Cool. So this is the first way that you can do this to find this transformation of z to being x plus y. So this is the first way that you can do it using the normal definition of your CDF like that. And then the next way, the next method is what I want us to quickly just focus on a little bit, right? It has a little conditions. So you will be given z is equal to your x plus y like this, right? Or maybe they'll say z is equal to x plus y, and then you also get maybe w is equal to y like this. So there are two cases that can happen, that either they will give you that z is equal to x plus y, and then they also give you that w is equal to y, okay? Or maybe they'll just give you that z is equal to x plus y. So it's then up to you that, okay, either you can answer this the way we did earlier on, where you're just going to use the definition of your CDF and carry on to answer the question, or you can then introduce a dummy variable w being either equal to y, or you can even make it equal to x, right? You can make it anything you want, but by just simply letting it equal to one of the variables, right, makes it quite easier for you to handle, right? So this is the case where now we have u being equal to that, and we have v being equal to that, right? Because as you can see, now we have two random vectors which are both in terms of x and y, though this one other one does not have x and y, but yeah, you can just, because it's a dummy variable and you want to be as simple as possible, you do that. But if you wanted, you can even introduce a dummy variable, which is y is equal to y, w is equal to y minus x, right? This will still work as well, but just having one there will make it much more easier to deal with that when you are dealing with two things, right? Now, there are a few conditions for you to apply the method that you will use to answer such a question, right? The first is that obviously you have here, the first one is that you have some function u equal to g of x, y, and you have some h, you have some v equal to h x of y, which in this case we have it. Though it's just z and w, but the point is we have these two things here which are in terms of your x and y. Even though, like I said, this does not necessarily have to have the x there, you can just have your w as thing equal to x, right? And the next thing is that you can find inverses. You can find inverse of each. What it means is that you're able to write, even though you've got z is equal to this and you've got w is equal to that, you need to be able to write each. Like you need to have an equation for x and an equation for y. What I mean is that in a case where I had z being equal to that and w just being equal to that, the second condition is telling us that you need to be able to then say, okay, I have my y being equal to w, and I also have my z is equal to x plus y, which I can write as my x being equal to z minus y, but since my y is equal to w, this is equal to z minus w. So the second condition says that then after you know that you've got these two random vectors, the second thing, you need to be able to write your x and your y each in terms of the random vectors that you have. Because as you can see, now what I have is my x being equal to w, and my y is equal to w, my x is z minus w, right? Which are both in terms of these random vectors that we have there, but no longer in terms of each of the random variables on the right side, as you can see there. Then the next thing is that you need to be able to find the Jacobian, right? You need to find the Jacobian, and this Jacobian must be not equal to 0, right? It can be negative, but not equal to 0. And the Jacobian is described as follows, because remember now you have your x being equal to z minus w, and you have your y being equal to w, right? So now your Jacobian is described as follows. This is you taking a derivative of x, right? Because you have this function x is equal to that. You first take its derivative with respect to, okay, I'm going to use this now here, these vectors, right? I don't want to stick to the z and w, but you will take with respect to u first, then here x with respect to v, then you got your y with respect to u, your y with respect to v. like that. So that's what you do. But the condition is saying that this Jacobian must not be 0. It has to be non-zero. So it can either be negative, but it just must not be 0. It can be negative or positive, but it's not equal to 0. So the formula, if I can call it a formula, tells us that now, if this is the case, that these conditions are satisfied, then for you to find the joint PDF of your U and V, because remember, that's what we wanted. We want the PDF of U and V. Right? We have the U being equal to G X of Y, and we have V being equal to H X of Y, and this is what we want. So having met all those conditions that we mentioned earlier on, then you can conclude that your PDF of U and V, right? Your U and V will simply just be equal to the PDF, the joint PDF of your X and Y that you had, right? But wherever in that PDF there is an X, you are going to write the X, but in terms of the U and V, and wherever there's a Y, you write that Y in terms of U and V, and after that, you are going to multiply with your Jacobian, right? So remember, the case earlier, the scenario I gave earlier on, an example of a scenario where we had our X being equal to Z minus W, and our Y being equal to W, right? What this statement is saying is that if maybe your joint PDF of X and Y was equal to e to the power minus Y minus X, like that, wherever there's a Y, I will no longer be writing Y, because remember again, if I'm trying to find the PDF of my U and V, it means that my function should also just be in terms of U and V, not X. So this formula is saying wherever there's an X, you're going to write this X that you got here now. Wherever there's a Y, you write this. That is, you will have e to the power minus, where there's a Y, I'll write a W, minus, where there's X, I'll have Z minus W, like that, right? So that's what this formula is basically saying. And when you're done, you multiply with the positive of your determinant, your Jacobian. You have gotten your Jacobian, and remember, like we said earlier on, the Jacobian does not need to be positive or negative, but just non-zero. But when you then come to apply it here on your formula, you take the positive of it, because the Jacobian there is not supposed to influence on whether your PDF is positive or negative. Thus, having it being positive will not affect that. But if it was negative and the PDF is maybe negative already, that can then affect whether it's positive or negative. So you always just need the positive of your Jacobian. Okay? And just this, yeah, so especially in a case where it's exponentials, that's the most popular question under this that I've come across, where your X and Y are exponentials. Hence, I even used this here. I think I still remember from a question I saw where an exponential with your lambda both equal to 1 and whatnot, right? And okay, I understand that we are above time already, but I just want to quickly just discuss this one quick thing here, that the probabilities, we've already covered something similar now when we're dealing with the CDF. But suppose you're given your X and Y, and obviously you have more information, maybe X and Y are exponentially distributed, like I'm saying, let's see. Oh, did I have FXW? No, like I think what I meant to write was FXY. I'm sorry, FXY. Let me write that quickly down again here. I think what I meant to write was FXY. So I was saying my PDF of FUV, right, which is what we're trying to find, will now be equal to FXY, and then X in terms of U and V, Y, U and V, D, X, like that. That's what I meant. So yeah, the W was a mistake there. This is just saying the PDF of X and Y, which you should have based on the information they've been given earlier on. Either that they give you the PDF on its own, or that maybe they just give you that Y and your X are independent. So are exponential, independent exponentials, and thus you just multiply their marginal PDFs and stuff. That was my bet there. It was supposed to be Y and not W. Cool. So what I wanted to consider to us to just quickly, as we close, is that if you're asked to find the probability maybe that x plus y, 2x plus y is less or equal, is less than 1, for example, right? And obviously, this is me assuming, it's not a complete question. This is me assuming that you're given information about x and y, and somehow you're able to find the PDF either by multiplying marginals if they're independent, like I keep on saying, or maybe it was given to you, or maybe you need to find the CDF of your x and y together, then you find your derivatives, find your PDF. But either way, you've got information about your x and y's. Now they ask you to find the probability that 2x plus y is less than 1. This one here, you would do it the same way that we did when we were finding the CDF, right? Remember when we were finding the CDF, we had to draw a line. So this would require you taking what you have there inside the probability function for you to draw a line, right? So the line that you would have in this case here will be something which is you have 2x, right, plus y, right? For now, I'll take this as just being equal to 1, because what I want is just for us to have some line that we are going to draw. You make your y the subject of the formula. That is y is equal to 1 minus 2x, like that. Then all you have to do from that is for you to draw the line y is equal to 1 minus 2x, right? You find your x-intercept, you find your y-intercept, and if you do that, you find that your y-intercept should be 1, your x-intercept should be something that is half, and then you would draw a line like this, right? And then this was saying that this has to be less than, so you'll be considering this region here. That's the region that we are looking at, and all you then have to do, using that small formula that I wrote earlier on, remember, I wrote something which was saying the probability that your x and your y here are an element of some region is simply just equal to the double integration on some region of what are you integrating. This will be a joint PDF of your x and y with respect to x, respect to y, and this here depends on whatever you prefer to start with or to end with. But a small guide is that, remember again, as much as you're going to draw lines like this here to see how your x are moving and your y is moving, what you want is that the outer bound should be something that's a constant, right? Because you want an answer. This is asking for a probability, which means whatever answer you should have at the end is something that's between 0 and 1, right? So if I were to simplify this further here, from there to this part here, this should be equal to something. If you were to look at the bounds, this would be 0 to 1, and this would be 0 to 1 minus 2x. And what you'll be integrating there will be your PDF of x, your joint PDF of x, right? And you'll be doing this with respect to, I started with x, right? Because my x is moving from here to that line there, which is 1 minus 2x. And the reason it's 1 minus 2x is because it's in terms of x, so I don't want it to be in terms of, I don't want any y there, hence I have my 1 minus, okay, no, it's not supposed to be, this is, 2x. This is not supposed to be like this, because it's, with respect to x, whatever I have here must not be in terms of x, which means that I need to make x the subject of the formula. So we have y being equal to 1 minus 2x. So I have y minus 1 being equal to minus 2x. So my x will actually just, in fact, be 1 minus y over 2. So what I would have is 1 minus y over 2, like that. And then, yeah, cool. And then with respect to y, I'll look at my y, and remember, what we want is for one of them to be in terms of with the constant. Okay, hold on. Just want to read the question here. What does it mean? Oh, there's a question there which is asking what it means for our Jacobian to be equal to 0, right? As far as to what it means, I feel like okay, you definitely explain more in maths. But in the case of our questions that we're dealing with here, the moment this is equal to, it's equal to 0, it means you cannot choose the formula. You have to find other means to actually solve the question, right? So the important thing is that the moment the Jacobian there is equal to 0, then you can't use the formula. You have to use other ways like we're looking at. But if your Jacobian is non-zero, then you can apply the formula. And then basically to finish up this question, then you just have to do the integration again as we did earlier on. And then that will be just about it. Yeah, I think that's done. Like for those that are still in the group, like just give me some reaction, just to know that you guys are okay. as you go and rest. And I'm sorry about what happened when we were starting. I don't know. It was my first time as well doing a workshop like this, and yeah, but I hope it was helpful, and I hope to see you again next time. So cheers, guys.